Before stars, before space, before time itself, there was nothing. Or maybe something. Then suddenly everything began. In a tiny fraction of a second, the universe exploded into being. It was hot, dense, and full of energy. This is what we call the Big Bang. But if the Big Bang created the universe, what caused the Big Bang? Scientists have searched for answers for decades. They've found ancient light still travelling through space. They've seen galaxies moving apart and time stretching like rubber. In 1964, they discovered a strange glow coming from every direction, a leftover signal from the beginning. But even now, the moment before the Big Bang remains a mystery. Could there have been something before everything? And if so, what? Before we begin the journey, let us know where in the world you're watching from and what time it is for you right now. Post it in the comments below and settle in for a fascinating ride through space. The story of the universe, as understood by modern science, begins not with an explosion in space, but with the expansion of space itself from an incredibly hot, dense state. This foundational idea is known as the Big Bang theory. It describes how our universe evolved from its earliest moments to the vast, complex cosmos we observe today. The theory does not attempt to explain what existed before this moment, nor what caused it, but rather provides a comprehensive framework for the universe's development after its initial state. It is a scientific model, built upon a bedrock of observational evidence and theoretical predictions, which has been refined over many decades. The conceptual seeds of the Big Bang theory were sown in the early 20th century, a time of profound shifts in scientific thought. Albert Einstein's theory of general relativity, published in 1915, revolutionized our understanding of gravity, space, and time. It proposed that gravity is not a force acting at a distance, but rather a curvature of space-time caused by mass and energy. When scientists began to apply Einstein's equations to the entire universe, they found that a static, unchanging universe, as was commonly believed at the time, was unstable. Einstein himself initially added a cosmological constant to his equations to force a static solution, a decision he would later call his biggest blunder. Independent of Einstein's initial preference for a static universe, several scientists began to explore the implications of a dynamic cosmos. In 1922, Russian physicist Alexander Friedmann developed solutions to Einstein's equations that described an expanding universe. His work, however, was not widely known in the West at the time. The crucial observational evidence began to emerge from the realm of astronomy. Vesto Slipher, an American astronomer, had been observing the spectra of spiral nebulae, which we now know are galaxies, since 1912. He found that most of these nebulae were moving away from Earth at very high speeds, indicated by a shift in their light towards the red end of the spectrum, a phenomenon known as redshift. It was a Belgian priest and physicist, Georges Lemaître, who, in 1927, independently derived the expanding universe solutions from general relativity and crucially connected them to Slipher's observations. Lemaître proposed that the universe began from a single, extremely dense point, which he called the primeval atom. He suggested that this atom then expanded and diversified, eventually forming the universe we see. His work, initially published in an obscure Belgian journal, gained wider recognition when translated into English in 1931. The most compelling observational evidence came from the American astronomer Edwin Hubble. Working at the Mount Wilson Observatory in California, Hubble, along with his assistant Milton Humason, made groundbreaking measurements of the distances to these spiral nebulae. By 1929, Hubble announced his discovery. The further away a galaxy was, the faster it appeared to be moving away from us. This relationship, now known as Hubble's law, provided powerful empirical support for the idea of an expanding universe. If everything is moving away from everything else, it implies that, in the past, everything must have been much closer together. This was a pivotal moment, shifting the scientific consensus from a static to a dynamic universe. The term Big Bang itself was coined in 1949 by British astronomer Fred Hoyle during a BBC radio broadcast. Hoyle was a proponent of the rival steady-state theory. which proposed that the universe was eternal and unchanging, with new matter continuously being created to fill the gaps left by expansion. Hoyle used Big Bang somewhat derisively to describe Lemaitre's theory, intending to ridicule its seemingly abrupt beginning. Ironically, the catchy name stuck and became the widely accepted term for the theory it was meant to discredit. While the observational evidence for expansion mounted, theoretical work continued to strengthen the Big Bang model. In the 1940s, George Gamow, along with his students Ralph Alpher and Robert Herman, made key predictions based on the hot, dense early universe. They reasoned that if the universe started from such extreme conditions, it would have been hot enough for nuclear fusion to occur in its earliest moments, leading to the formation of light elements like hydrogen and helium in specific proportions. Furthermore, they predicted that the residual heat from this early hot phase should still be detectable today, as a faint glow of microwave radiation permeating the entire universe. This prediction, made in 1948, would become one of the most significant pieces of evidence for the Big Bang. The accidental discovery of this cosmic background radiation in 1964 by Arno Penzias and Robert Wilson at Bell Labs provided the smoking gun. They were working with a new horn antenna and kept detecting a persistent uniform static or noise that they could not eliminate. It came from every direction in the sky, regardless of the time of day or year. Simultaneously, researchers at Princeton University, led by Robert Dick, were independently searching for this very radiation, unaware of Penzias and Wilson's discovery. When the two groups connected, it became clear that Penzias and Wilson had stumbled upon the cosmic microwave background, CMB, the faint afterglow predicted by Gamow and his colleagues. This discovery effectively sealed the fate of the steady-state theory and cemented the Big Bang as the leading cosmological model. The Big Bang theory, therefore, is not a description of an explosion that happened at a specific point in space, with matter flying outwards into an empty void. Instead, it describes the expansion of space itself, carrying galaxies and all matter along with it. Imagine a balloon being inflated. Dots drawn on the surface move further apart as the balloon expands, but no single dot is at the centre of the expansion, and the dots are not moving through the balloon's surface, but rather the surface itself is growing. Similarly, in the universe, every point appears to be the centre of the expansion, and galaxies are not rushing through pre-existing space, but the fabric of space-time between them is stretching. This stretching causes the light from distant galaxies to be redshifted, providing the primary observational evidence for this ongoing cosmic expansion. Over the decades, further observations and theoretical advancements have continued to refine and support the Big Bang model. The observed abundances of light elements in the universe, such as hydrogen, helium, and lithium, precisely match the predictions made by the Big Bang nucleiosynthesis theory, which describes element formation in the first few minutes after the Big Bang. The large-scale structure of the universe, with its vast cosmic web of galaxies and voids, also aligns with predictions from the Big Bang model, especially when combined with the concept of dark matter and dark energy. While the Big Bang theory provides an incredibly successful framework for understanding the universe's evolution from a tiny fraction of a second after its beginning, the question of what initiated this expansion, or what existed before, remains a profound area of ongoing scientific inquiry and speculation. One of the most profound and counterintuitive aspects of observing the universe is that when we look out into space, we are simultaneously looking back in time. This seemingly magical ability is not due to any special properties of our telescopes, but rather a fundamental consequence of the finite speed of light. Light, the fastest thing we know, travels at a specific, measurable speed through the vacuum of space. This speed is approximately 300,000 kilometers per second, or about 186,000 miles per second. While this speed seems incredibly fast in our everyday experience, the distances in the cosmos are so immense that light takes a considerable amount of time to travel from its source to our eyes or our instruments. Consider the most familiar example, the Sun. The light we see from the Sun left its surface approximately 8 minutes and 20 seconds ago. This means that if the Sun were to suddenly vanish, we would not know about it for over 8 minutes. We're always seeing the Sun as it was in the recent past, not as it is in the present moment. This principle extends to every object we observe in the universe. The further away an object is, the longer its light has been travelling to reach us, and consequently, the further back in time we are seeing it. To manage the immense distances involved in astronomy, scientists use a unit called the light year. A light year is not a measure of time, but a measure of distance. It is the distance that light travels in 1 Earth year. This distance is approximately 9.46 trillion kilometres, or about 5.88 trillion miles. Using this unit, we can grasp the scale of the cosmos. For instance, the nearest star to our solar system, Proxima Centauri, is about 4.2 light-years away. This means that the light we receive from Proxima Centauri left that star 4.2 years ago. We are seeing it as it was 4.2 years in the past. Now, extend this concept to galaxies. The Andromeda Galaxy, our closest large galactic neighbour, is about 2.5 million light-years away. When we gaze at the Andromeda Galaxy through a telescope, we are seeing light that began its journey 2.5 million years ago. This light originated when early humans were just beginning to evolve on Earth. The implications are staggering. Every image of a distant galaxy is a snapshot from the past. This principle is the cornerstone of observational cosmology, allowing astronomers to piece together the history and evolution of the universe. Telescopes, in essence, become time machines. By observing objects at progressively greater distances, we are effectively looking at different epochs in cosmic history. The most powerful telescopes, like the Hubble Space Telescope and more recently the James Webb Space Telescope, are designed to peer deep into the universe, capturing light from objects billions of light-years away. For example, when astronomers observe galaxies that are 10 billion light-years away, they are seeing those galaxies as they appeared 10 billion years ago, when the universe was only a few billion years old. At these immense distances, we are observing the universe in its infancy. We can see the earliest, most primitive galaxies, which look very different from the mature, well-formed spiral and elliptical galaxies we see closer to us. These early galaxies are often smaller, more irregular, and undergoing rapid bursts of star formation. By comparing these ancient galaxies with closer, younger ones, scientists can trace the evolutionary pathways of galaxies over cosmic time. The furthest back in time we can see with a light is to the cosmic microwave background, CMB radiation. This faint glow, detected across the entire sky, is light that was emitted approximately 380,000 years after the Big Bang, when the universe had cooled enough for the first stable atoms to form. Before this time, the universe was so hot and dense that light could not travel freely. It was constantly scattered by free electrons and protons, making the universe opaque, like a dense fog. When the universe cooled and atoms formed, electrons combined with nuclei, and the universe became transparent. The light from that moment, now stretched and cooled by billions of years of expansion, is what we detect as the CMB. It represents the baby picture of the universe, the oldest light we can ever hope to observe directly. Beyond the CMB, our understanding relies purely on theoretical models, as no light from earlier epochs can reach us. However, the CMB itself provides invaluable information about the conditions of the early universe, including its temperature, composition, and slight variations in density that eventually grew into the large-scale structures we see today. Different types of telescopes allow us to observe different wavelengths of light, each revealing unique aspects of the universe's past. Optical telescopes observe visible light, showing us stars and galaxies as we typically imagine them. Radio telescopes detect radio waves, which can penetrate dust clouds and reveal regions of star formation or distant active galaxies. X-ray telescopes observe high-energy X-rays, allowing us to study phenomena like black holes and hot gas in galaxy clusters. Each wavelength provides a different window into the past, painting a more complete picture of cosmic evolution. The ability to look back in time is not just a fascinating curiosity, it is a critical tool for testing and refining cosmological models, including the Big Bang theory. If the Big Bang theory is correct, then the universe should have looked different in the past, and these differences should be observable. The fact that we see galaxies evolving over time, the presence of the CMB, and the distribution of light elements all provide strong confirmation of the universe's dynamic history, as described by the Big Bang model. Without the finite speed of light and our ability to measure and interpret it, our understanding of the universe's origins and evolution would be vastly more limited, confined to only the present moment of cosmic existence. The expansion of the universe is not something we can directly see in the way we observe an object moving away from us in everyday life. Instead, scientists infer this expansion from a crucial piece of evidence: the redshift of light from distant galaxies. To understand redshift, we first need to briefly consider the nature of light itself. Light is a form of electromagnetic radiation, which travels in waves. Like all waves, light waves have a wavelength, the distance between two consecutive crests or troughs, and a frequency, the number of waves that pass a point in a given amount of time. The colour of visible light depends on its wavelength. Red light has the longest wavelength, while violet light has the shortest. The phenomenon of redshift is an example of the Doppler effect, which is familiar from sound waves. Imagine an ambulance siren. As the ambulance approaches you, the sound waves are compressed, leading to a higher pitch. As it moves away, the sound waves are stretched out, resulting in a lower pitch. The same principle applies to light waves. If a light source is moving towards an observer, the light waves it emits are compressed, causing their wavelength to shorten. This shift towards shorter, bluer wavelengths is called blue shift. Conversely, if a light source is moving away from an observer, the light waves are stretched, causing their wavelength to lengthen. This shift towards longer, redder wavelengths is called redshift. In astronomy, redshift is a critical tool. When astronomers analyze the light from stars and galaxies, they use a spectroscope to break the light down into its component colors, creating a spectrum. This spectrum contains dark lines or bright lines at specific wavelengths, which are like fingerprints of the chemical elements present in the star or galaxy. For example, hydrogen atoms absorb or emit light at very precise known wavelengths. If a galaxy is moving away from us, these characteristic spectral lines will be shifted towards the red end of the spectrum, compared to where they would be if the galaxy were stationary. The amount of this redshift directly tells us how fast the galaxy is receding. The systematic observation of redshift in distant celestial objects began in the early 20th century. Vesto Slipher, an American astronomer at the Lowell Observatory, was one of the pioneers in this field. Starting in 1912, he meticulously measured the radial velocities, motion towards or away from us, of various spiral nebulae, which were then thought to be gas clouds within our own Milky Way galaxy. To his surprise, Slipher found that the vast majority of these nebulae were exhibiting significant redshifts, meaning they were moving away from Earth at tremendous speeds. By 1917, he had measured the velocities of 25 nebulae, and only a few showed blue shift. This was a puzzling observation at the time, as it implied a general outward motion from our position. The true significance of Slipher's redshifts became clear with the work of Edwin Hubble. Working at the Mount Wilson Observatory in California in the 1920s, Hubble made two monumental contributions. First, he definitively established that many of these spiral nebulae were not gas clouds within our galaxy, but were, in fact, independent galaxies far beyond the Milky Way. He did this by identifying a type of variable star called Cepheid variables in some of these nebulae, which allowed him to accurately determine their distances. Second, and most crucially for the Big Bang theory, Hubble combined his distance measurements with Slipher's velocity measurements. In 1929, he announced his groundbreaking discovery. There was a direct relationship between a galaxy's distance from us and its recession velocity. The further away a galaxy was, the faster it was moving away. This relationship is now famously known as Hubble's law. It can be simply stated as velocity equals Hubble's constant multiplied by distance. This linear relationship was a profound revelation. It was not just that things were moving away, but that the rate of their recession increased with distance. Hubble's law provided the strongest observational evidence yet for an expanding universe. If all galaxies are moving away from each other, and the further ones are moving faster, it implies that the space between them is stretching. It's crucial to understand that this is not like an explosion, where fragments fly outwards from a central point. Instead, it's the fabric of space itself that is expanding, carrying the galaxies along with it, much like dots drawn on the surface of an inflating balloon. As the balloon expands, the dots move further apart, but no single dot is at the centre of the expansion, and the dots themselves are not moving on the surface, but the surface itself is growing. Similarly, in the universe, there is no central point of expansion. Every observer, no matter where they are located, would see all other galaxies receding from them. The redshift observed in distant galaxies is therefore not just a measure of their speed through space, but a cosmological redshift, caused by the stretching of the light waves as the space they travel through expands. As the universe expands, the wavelength of the light travelling through it gets stretched, making it appear redder by the time it reaches our telescopes. This cosmological redshift is a direct signature of the universe's ongoing expansion. The discovery of the redshift distance relationship, formalized as Hubble's law, provided powerful support for the Big Bang model, which inherently predicts an expanding universe. It showed that the universe is not static but dynamic and evolving. The rate of this expansion, quantified by Hubble's constant, also allows scientists to estimate the age of the universe. By running the movie backward, if we know how fast things are expanding now, we can calculate how long it would have taken for everything to have been compressed into a very small, dense state. Current estimates, based on the most precise measurements of the Hubble constant and other cosmological parameters, place the age of the universe at approximately 13.8 billion years. The universe, as described by the Big Bang theory, began in an incredibly hot and dense state. As it expanded, it cooled. A crucial prediction of this model, made decades before its discovery, was that the residual heat from this early fiery period should still be detectable today as a faint uniform glow of microwave radiation permeating all of space. This ancient light, often called the cosmic microwave background, or CMB, is the most compelling single piece of evidence supporting the Big Bang. It is essentially the universe's baby picture, showing us what the cosmos looked like when it was only a few 100,000 years old. The idea that such radiation might exist dates back to the 1940s. George Gamow, along with his students Ralph Alpher and Robert Herman, were working on the theory of Big Bang nucleiosynthesis, which describes how the first light elements were formed in the early universe. Their calculations indicated that if the universe had been hot and dense enough to fuse hydrogen into helium in its first few minutes, it must have been filled with intense radiation. As the universe expanded and cooled over billions of years, this radiation would have stretched to longer wavelengths, eventually becoming microwaves. In 1948, Alpher and Herman specifically predicted that this leftover radiation should have a temperature of about 5 Kelvin, or 5 degrees above absolute zero, a temperature that would correspond to microwave wavelengths. Their prediction, however, went largely unnoticed by the broader scientific community for many years. For the first 380,000 years after the Big Bang, the universe was a scorching hot, opaque plasma. It was so hot that electrons were not bound to atomic nuclei. Instead, free electrons and atomic nuclei, mostly protons and helium nuclei, moved independently. Light or photons could not travel far in this environment without colliding with these free electrons. Imagine trying to walk through an extremely dense fog. You can only see a short distance. The early universe was like this, but for light. Photons were constantly scattering off the charged particles, making the universe effectively opaque. This period is often referred to as the photon epoch. As the universe continued to expand, it cooled. When the temperature dropped to approximately 3000 Kelvin, a critical event occurred. This was about 380,000 years after the Big Bang. At this temperature, the free electrons had slowed down enough to be captured by the atomic nuclei, forming the first stable neutral atoms, primarily hydrogen and helium. This process is known as recombination, though it is a bit of a misnomer because electrons and nuclei were combining for the first time, not recombining. With the electrons now bound within atoms, they were no longer free to scatter photons. Suddenly the universe became transparent to light. The photons that had been trapped and constantly scattering were now free to travel across the cosmos without interruption. These are the photons we detect today as the cosmic microwave background. Over the subsequent 13.8 billion years, as the universe continued its vast expansion, These photons have travelled immense distances. The expansion of space has stretched their wavelength considerably. What was once visible or near-infrared light, with a temperature of 3000 Kelvin, has been stretched so much that its wavelength is now in the microwave portion of the electromagnetic spectrum. Its temperature has cooled to a mere 2.725 Kelvin, or about 2.725 degrees above absolute zero. This is why it is referred to as microwave background radiation. The actual discovery of the CMB was serendipitous. In 1964, two American radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Telephone Laboratories in Holmdel, New Jersey. They were testing a new, highly sensitive horn antenna designed for satellite communication and radio astronomy. Their goal was to eliminate all sources of noise from their receiver. They meticulously checked their equipment, removed pigeon droppings from the antenna, and even considered the possibility of radar from New York City. Despite their best efforts, they kept detecting a persistent uniform low-level static, or hiss, that came from every direction in the sky, day and night, regardless of the time of year. It was a faint, steady signal that they could not explain or eliminate. Unbeknownst to Penzias and Wilson, a group of physicists at Princeton University, led by Robert Dicke, along with James Peebles, P.G. Roll and David Wilkinson, were independently working on the theoretical implications of the Big Bang. They had in fact rediscovered the prediction made by Gamow, Alpha and Herman, that if the universe began with a hot Big Bang, there should be a faint uniform background of microwave radiation left over. The Princeton team was actually building an antenna to search for this very signal. Through a chance phone call, Penzias learned about Dicke's work, and Dicke learned about Penzias and Wilson's unexplained noise. The connection was immediately clear. Penzias and Wilson had accidentally discovered the cosmic microwave background, the ancient echo of the Big Bang. Their discovery, published in 1965, earned them the Nobel Prize in Physics in 1978. The CMB is incredibly uniform across the entire sky, with variations in temperature of only about 1 part in 100,000. This uniformity is a strong confirmation of the Big Bang's initial homogeneity. However, the tiny variations, or anisotropies, are equally important. These slight temperature differences represent minuscule density fluctuations in the early universe. These tiny ripples, amplified by gravity over billions of years, eventually grew into the vast cosmic structures we see today, such as galaxies, clusters of galaxies, and the large-scale cosmic web. Without these initial seeds of inhomogeneity, the universe would be a featureless, uniform expanse of gas. Subsequent dedicated missions have provided increasingly precise measurements of the CMB. The Cosmic Background Explorer, or COBE satellite launched by NASA in 1989, confirmed that the CMB has a perfect blackbody spectrum, exactly as predicted for thermal radiation from the early universe. This was a crucial test. COBE also detected the tiny temperature fluctuations, providing the first clear evidence of the seeds of cosmic structure. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, provided much higher resolution maps of these fluctuations, allowing scientists to determine key cosmological parameters with unprecedented accuracy, including the age of the universe, its composition of ordinary matter, and dark energy, and the geometry of space. Most recently, the European Space Agency's Planck satellite, launched in 2009, produced the most detailed maps of the CMB to date, further refining these measurements and providing even tighter constraints on cosmological models. The cosmic microwave background is not just a relic, it is a powerful probe of the early universe. Its existence, its blackbody spectrum, its uniformity, and its tiny anisotropies all align perfectly with the predictions of the Big Bang theory. It provides a direct observational window into the universe when it was only 380,000 years old, long before the first stars and galaxies had formed. It confirms the universe was once hot, dense, and opaque, and that it has been expanding and cooling ever since. Without the discovery and detailed study of the CMB, the Big Bang theory would remain a compelling hypothesis, but with it, it stands as the overwhelmingly accepted scientific model for the evolution of our cosmos. The Big Bang theory not only explains the expansion of the universe and the existence of the cosmic microwave background, but it also provides a precise account for the observed abundance of the lightest chemical elements in the cosmos. The universe, as we observe it today, is overwhelmingly composed of hydrogen and helium, with trace amounts of lithium. The Big Bang theory accurately predicts the specific proportions of these elements, a process known as Big Bang nucleosynthesis, or BBN. This agreement between theoretical prediction and observational fact serves as another powerful pillar supporting the Big Bang model. To understand BBN, we must go back to the very early universe, specifically the first few minutes after the Big Bang. At this time, the universe was incredibly hot and dense, far too hot for stable atomic nuclei to form. Instead, it was a rapidly expanding and cooling soup of fundamental particles: protons, neutrons, electrons, positrons, neutrinos, and photons. The temperature was so extreme, reaching billions of degrees Kelvin, that protons and neutrons could freely convert into one another. The balance between protons and neutrons was primarily determined by the universe's temperature and the slight mass difference between them. As the universe cooled, the conversion of neutrons to protons became less favourable, leading to a slight excess of protons. For every 7 protons, there was approximately 1 neutron. This ratio is crucial for the subsequent formation of light elements. The actual process of nucleosynthesis began when the universe was only about 1 second old and had cooled to a temperature of about 10 billion Kelvin. At this point, the strong nuclear force, which binds protons and neutrons together, became effective. However, the universe was still hot enough that any newly formed atomic nuclei would be immediately broken apart by high-energy photons. This situation is often referred to as the deuterium bottleneck. Deuterium, an isotope of hydrogen with 1 proton and 1 neutron, is the first step in the formation of heavier elements. But at temperatures above approximately 900 million Kelvin, deuterium nuclei are instantly shattered by energetic photons. Nucleosynthesis could only truly begin when the universe had cooled sufficiently to overcome this deuterium bottleneck. This occurred when the universe was roughly 3 minutes and 46 seconds old, and its temperature had dropped to around 900 million Kelvin. At this temperature, deuterium nuclei could finally survive long enough to fuse further. Once deuterium formed, it quickly combined with other protons and neutrons to build up heavier nuclei. The primary reactions during BBN involved deuterium fusing with protons to form helium-3, and then helium-3 fusing with other nuclei to form helium-4. Helium-4, with 2 protons and 2 neutrons, is an exceptionally stable nucleus, and it was the main product of Big Bang nucleosynthesis. The process was very efficient at converting almost all available neutrons into helium-4. Since there was roughly 1 neutron for every 7 protons, and each helium-4 nucleus requires 2 neutrons, this meant that for every 2 neutrons, there would be 2 protons to form 1 helium-4 nucleus. The remaining 6 protons would stay as individual hydrogen nuclei. This leads to a predicted mass ratio of about 75% hydrogen and 25% helium-4. Beyond helium-4, only trace amounts of other light elements were formed. Some helium-3 and deuterium nuclei did not fuse into helium-4 and remained in their original state. A tiny fraction of lithium-7 was also produced, primarily through the fusion of helium-4 and helium-3, or from the decay of beryllium-7. However, the conditions in the early universe were not suitable for the formation of elements heavier than lithium. The universe was expanding and cooling too rapidly. By the time heavier nuclei like carbon or oxygen could have formed through further fusion reactions, the temperature and density had dropped too low, and the nuclear reactions effectively ceased. All the heavier elements we see today, from carbon to iron and beyond, were forged much later in the cores of stars through stellar nucleosynthesis and supernova explosions. The remarkable aspect of Big Bang nucleosynthesis is the precision with which its predictions match observations. Astronomers measure the abundance of these light elements in the most pristine ancient environments they can find in the universe. This includes distant quasars, which are powered by supermassive black holes in early galaxies and old metal-poor stars in the halos of galaxies. These environments are chosen because they have undergone minimal stellar processing. That is, their material has not been significantly altered by the nuclear fusion processes occurring in stars, which would change the elemental compositions. The observed cosmic abundance of helium-4 is consistently found to be around 24 to 25% by mass, which aligns almost perfectly with the BBN predictions. The abundance of deuterium is also a crucial test. Because deuterium is easily destroyed in stellar interiors, its primordial abundance is a sensitive probe of the conditions during BBN. Observations of deuterium in distant gas clouds, illuminated by quasars, show an abundance that is also in excellent agreement with the Big Bang model's predictions. Similarly, the observed amount of lithium-7, though subject to some complexities in measurement and theoretical understanding, generally falls within the expected range. The success of Big Bang nucleosynthesis in predicting the primordial abundances of light elements is a powerful validation of the Big Bang model. It demonstrates that the universe was indeed hot and dense enough in its early stages for these nuclear reactions to occur, and that it cooled and expanded at a rate consistent with the observed cosmic expansion. Furthermore, the precise values of these abundances are sensitive to the amount of ordinary matter, or baryonic matter, in the universe. The agreement between BBN predictions and observations allows cosmologists to determine the density of baryonic matter in the universe, which is found to be only about 4 to 5% of the total mass-energy content. This finding provides independent evidence for the existence of dark matter and dark energy, which constitute the vast majority of the universe's mass and energy, respectively. In essence, the light elements serve as fossil records from the universe's infancy. Their measured proportions across the cosmos are a direct consequence of the physical conditions that existed just minutes after the Big Bang. The fact that the Big Bang theory can explain these abundances with such accuracy provides a compelling and quantitative confirmation of its validity, reinforcing its position as the leading scientific explanation for the origin and evolution of our universe. The very first moments of the universe, immediately following the Big Bang, represent a period of extreme conditions where our current understanding of physics is pushed to its absolute limits. While direct observation of this epoch is impossible, theoretical models extrapolated from our knowledge of particle physics and general relativity allow us to paint a speculative yet scientifically informed picture of this unimaginably hot and dense beginning. This period encompasses timescales so brief they are difficult to comprehend, stretching from the Planck time to fractions of a second. The earliest conceivable moment we can discuss is the Planck epoch, which spans from time 0 up to approximately 10 to the power of minus 43 seconds after the Big Bang. At this incredibly tiny fraction of a second, the universe was compressed into a space smaller than a proton, and its temperature was an astounding 10 to the power of 32 Kelvin. In such extreme conditions, all four fundamental forces of nature — gravity, electromagnetism, the strong nuclear force, and the weak nuclear force — are thought to have been unified into a single superforce. Our current theories of physics, particularly general relativity, which describes gravity, and quantum mechanics, which describes the other three forces, break down at this scale. To fully understand the Planck epoch, a complete theory of quantum gravity is required, which scientists are still striving to develop. Theories like string theory and loop quantum gravity are attempts to bridge this gap. As the universe expanded and cooled slightly beyond the Planck time, gravity is thought to have decoupled or separated from the other three fundamental forces. This marked the beginning of the grand unification epoch, which lasted until approximately 10 to the power of minus 36 seconds. During this period, the strong, weak, and electromagnetic forces were still unified into a single, grand unified force. The universe was still extraordinarily hot and dense, but the temperature had dropped enough for distinct physical properties to begin to emerge. This epoch is also where the theory of cosmic inflation is often placed. Although inflation will be discussed in detail in another chapter, it is important to note its timing here. If it occurred, inflation was an incredibly brief period of exponential expansion, stretching the universe by a factor of at least 10 to the power of 26 in an almost unimaginably short time, perhaps from 10 to the power of minus 36 seconds to 10 to the power of minus 32 seconds. This rapid expansion would have smoothed out any initial irregularities and set the stage for the uniform and flat universe we observe today. Following the grand unification epoch, at around 10 to the power of minus 12 seconds, the universe entered the electroweak epoch. During this phase, the strong nuclear force separated from the electroweak force, leaving only the electromagnetic and weak nuclear forces still unified. The temperature had cooled to approximately 10 to the power of 15 Kelvin, which is still vastly hotter than the core of the hottest stars. At these energies, particles like quarks, leptons, such as electrons and neutrinos, and their antimatter counterparts were abundant. They existed in a hot, dense soup, constantly colliding and transforming into one another. A critical event during this early period, perhaps around 10 to the power of minus 11 seconds, was the breaking of the electroweak symmetry. This is when the electromagnetic force and the weak nuclear force separated, becoming the distinct forces we recognize today. This separation is associated with the Higgs mechanism, which gives mass to fundamental particles. Before this point, particles were massless, but after the electroweak symmetry breaking, they acquired mass through their interaction with the Higgs field. By approximately 10 to the power of minus 6 seconds, the universe had cooled to about 1 trillion Kelvin. This marked the beginning of the quark epoch, or hadron epoch. At this temperature, quarks, the fundamental building blocks of protons and neutrons, were still free and unconfined. The universe was filled with a hot, dense quark-gluon plasma, a state of matter where quarks and gluons, the particles that carry the strong force, moved freely, much like electrons in a metal. However, as the universe continued to expand and cool, the strong force became strong enough to bind quarks together. This process, called hadronization, occurred around 10 to the power of minus 6 seconds. Quarks combined to form composite particles called hadrons, primarily protons and neutrons. For every proton and neutron formed, there was also an antiparticle, antiproton and antineutron. A crucial puzzle in cosmology relates to this period, the matter-antimatter asymmetry. In the very early universe, matter and antimatter should have been produced in equal amounts. When matter and antimatter particles meet, they annihilate each other, converting their mass entirely into energy, photons. If matter and antimatter had been perfectly symmetrical, the universe would now be filled only with radiation, with no particles left to form stars, galaxies, or life. However, observations show that our universe is overwhelmingly composed of matter, with very little antimatter. Scientists believe that during these first moments, a tiny subtle asymmetry must have existed, perhaps 1 part in a billion, favouring matter over antimatter. This slight imbalance, known as baryogenesis, allowed a small residue of matter to survive the annihilation process, eventually forming everything we see today. The exact mechanism for this asymmetry is still an active area of research, potentially involving new physics beyond the standard model of particle physics. By 1 second after the Big Bang, the universe had cooled to about 10 billion Kelvin. At this point, the initial chaos had settled somewhat. The vast majority of matter-antimatter annihilation was complete, leaving behind the residual matter. Protons and neutrons were now stable, distinct particles. The universe was still too hot for atomic nuclei to form, but it was ready for the next crucial stage, Big Bang nucleosynthesis, where these protons and neutrons would begin to fuse into the first light elements, setting the stage for the formation of stars and galaxies billions of years later. The study of these first moments is highly theoretical, relying on the standard model of particle physics, which has been rigorously tested in particle accelerators like the Large Hadron Collider. While these accelerators cannot recreate the extreme energies of the very first instant of the Big Bang, they can probe conditions that existed fractions of a second later, allowing physicists to extrapolate backward in time with increasing confidence. Understanding these initial conditions is vital because they set the fundamental parameters for the universe's subsequent evolution, determining its composition, structure, and ultimate fate. The standard Big Bang model, while remarkably successful in explaining the universe's evolution from a very hot, dense state, faced several significant puzzles in the late 20th century. These challenges concerned observations of the universe's large-scale properties that seemed too finely tuned or too uniform to be explained by the standard model alone. To address these issues, a groundbreaking theoretical concept known as cosmic inflation was proposed. Inflation posits that the universe underwent an incredibly brief but extraordinarily rapid period of exponential expansion immediately after the Big Bang. This expansion was so powerful that it stretched the fabric of space itself by an immense factor, far exceeding the subsequent more gradual expansion we observe today. The idea of inflation was first proposed by American physicist Alan Guth in 1980, building on earlier work by others. Guth was initially trying to solve the problem of magnetic monopoles, hypothetical isolated magnetic charges predicted by some grand unified theories, which should have been abundant in the early universe but have never been observed. As he worked on this problem, he realized that a period of exponential expansion could solve not only the monopole problem, but also two other major cosmological puzzles, the flatness problem and the horizon problem. Let us first delve into the concept of this rapid expansion. Inflation is theorized to have occurred extremely early in the universe's history, perhaps starting as early as 10 to the power of minus 36 seconds after the Big Bang, and ending by about 10 to the power of minus 32 seconds. This means it lasted for an unimaginably short duration, less than a trillionth of a trillionth of a trillionth of a second. During this fleeting moment, the universe is believed to have expanded by a factor of at least 10 to the power of 26, and possibly much, much more. To visualize this, imagine a region of space smaller than a proton expanding to the size of a grapefruit in that minuscule time, or even larger. This expansion was driven by a hypothetical energy field, often called the inflaton field, which possessed unusual properties causing it to exert a repulsive gravitational force, effectively pushing space apart at an accelerating rate. When the inflaton field eventually decayed, its energy transformed into the hot, dense matter and radiation that filled the universe, initiating the standard Big Bang expansion we know. One of the key problems inflation solves is the flatness problem. Observations of the cosmic microwave background, CMB, have shown that the universe's geometry is remarkably flat. In cosmology, flat refers to a universe where the paths of parallel lines never converge or diverge, much like a flat piece of paper. A curved universe, by contrast, would be like the surface of a sphere, positive curvature, or a saddle, negative curvature. Einstein's theory of general relativity shows that the geometry of the universe depends critically on its total energy density. For the universe to be flat, its total energy density must be incredibly close to a specific critical density. Any deviation from this critical density, even a tiny one in the early universe, would have been magnified by expansion over billions of years, leading to a universe that was either very closed, curved like a sphere, and would have recollapsed quickly, or very open, curved like a saddle, and would have expanded so rapidly that structures could not form. The observed flatness is astounding, requiring the universe's initial density to be within 1 part in 10 to the power of 60 of the critical density. Inflation elegantly solves this. Just as stretching a wrinkled balloon to immense size makes its surface appear flat from any small section, inflation stretches any initial curvature of space so dramatically that the observable universe appears perfectly flat. The second major puzzle inflation addresses is the horizon problem. The cosmic microwave background radiation, which provides a snapshot of the universe when it was about 380,000 years old, appears remarkably uniform in temperature across the entire sky. This means that regions of the universe that are now separated by vast distances, so vast that light could not have travelled between them, even over the age of the universe, exhibit nearly identical temperatures. In the standard Big Bang model without inflation, these regions would have been causally disconnected. That is, they could not have exchanged information or heat. So, how did they come to have the same temperature? Inflation resolves this by proposing that all the regions we observe today originated from an incredibly tiny, causally connected patch of space before inflation began. This tiny patch was in thermal equilibrium, meaning it had a uniform temperature. Inflation then rapidly expanded this small, uniform region to astronomical scales, making it appear as if widely separated areas of the sky are in thermal contact, even though they are now beyond each other's light horizon. A third problem that inflation resolves is the magnetic monopole problem. Some grand unified theories, GUTs, which attempt to unify the strong, weak and electromagnetic forces at very high energies, predict the existence of magnetic monopoles, hypothetical particles that carry an isolated north or south magnetic pole, unlike conventional magnets which always have both. These monopoles would have been produced in vast quantities in the extremely hot early universe, and if they existed, they should be easily detectable today. However, despite extensive searches, no magnetic monopoles have ever been found. Inflation offers a solution. The rapid exponential expansion would have diluted the density of these monopoles to such an extent that their current number density in the observable universe would be virtually zero, making them effectively undetectable. Beyond solving these cosmological puzzles, inflation also provides a mechanism for the origin of structure in the universe. During inflation, tiny quantum-scale fluctuations in the inflaton field were stretched to macroscopic sizes. These microscopic quantum jitters, which are an inherent part of quantum mechanics, became macroscopic density variations. After inflation ended, these slight density enhancements acted as the seeds of cosmic structure. Over billions of years, gravity amplified these initial density differences, pulling more matter into the slightly denser regions, which eventually collapsed to form the first stars, galaxies, and the large-scale cosmic web we observe today. The pattern of these density fluctuations, as imprinted on the cosmic microwave background, is remarkably consistent with the predictions of inflation. For instance, CMB maps show a nearly scale-invariant spectrum of fluctuations, meaning that variations in density occurred on roughly all scales, which is a key prediction of inflationary models. The specific pattern of polarization in the CMB, particularly the B-mode polarization, is also a target for future observations, as it could provide direct evidence of gravitational waves generated during inflation. While inflation theory has become an integral part of the Big Bang model, and its predictions are strongly supported by observations from missions like COBE, BUMAP and Planck, it is important to remember that it is still a theory. The exact nature of the inflaton field remains unknown, and there are various different models of inflation. However, the basic framework of inflation provides such elegant solutions to fundamental cosmological problems that it is widely accepted by the scientific community as the leading extension to the standard Big Bang theory. It transforms the Big Bang from a moment of unexplained initial conditions into a more comprehensive narrative that addresses why the universe possesses the large-scale properties we observe. In the earliest moments of the universe, immediately following the Big Bang, the cosmos was a place of unimaginably extreme conditions. It was incredibly hot and dense, so much so that matter as we know it could not exist. Instead, the universe was filled with a fundamental soup of pure energy and elementary particles, constantly interacting and transforming into one another. This transformation from raw energy into the building blocks of all matter is a crucial part of the universe's early story. The foundation of this process lies in Albert Einstein's famous equation, E mc2, which describes the equivalence of mass and energy. This equation tells us that mass can be converted into energy, and, critically for the early universe, energy can be converted into mass. In the superheated environment of the very early cosmos, photons or particles of light carried enormous amounts of energy. When two sufficiently energetic photons collided, their energy could spontaneously convert into a pair of particles, a particle and its corresponding antiparticle. For instance, two high-energy photons could produce an electron and its antimatter twin, a positron. This process was happening constantly throughout the universe. So, in the first fractions of a second after the Big Bang, the universe was not empty space but a churning, seething plasma. This plasma was a dense mix of fundamental particles such as quarks, which are the building blocks of protons and neutrons, leptons, which include electrons and neutrinos, and their respective antiparticles, along with a vast sea of energetic photons. These particles were moving at relativistic speeds, meaning their speeds were a significant fraction of the speed of light, and they were constantly colliding, creating new particles and antiparticles, and then annihilating back into pure energy. Let us trace this process through time as the universe expanded and cooled. In the first instance, From the Planck epoch up to perhaps 10 to the power of -6 seconds, the universe was a quark-gluon plasma. At these extreme temperatures, individual quarks were not bound together. They existed freely, along with gluons, which are the force-carrying particles for the strong nuclear force that binds quarks. The universe was a hot, dense fluid where quarks and gluons moved independently, constantly being created and annihilated. As the universe continued to expand, its temperature rapidly dropped. Around 1 microsecond, 1/1,000,000th of a second after the Big Bang, the temperature had cooled to approximately 2 trillion Kelvin. At this critical temperature, the strong nuclear force became strong enough to confine quarks. This process is called hadronization. Quarks could no longer exist freely and instead bound together to form composite particles called hadrons. The most familiar hadrons are protons, which are made of 2 up quarks and 1 down quark, and neutrons made of 1 up quark and 2 down quarks. This was a pivotal moment, as the basic constituents of atomic nuclei were now formed. During this period of particle creation and annihilation, a fundamental imbalance played a critical role in the universe's ultimate fate: the matter-antimatter asymmetry. According to our current understanding, energy should have produced equal amounts of particles and antiparticles. For instance, every time an electron was created, a positron, anti-electron, should also have been created. When a particle encounters its antiparticle, they annihilate each other, converting their entire mass back into energy. If there had been a perfect balance between matter and antimatter, all of the particles and antiparticles produced in the early universe would have annihilated each other, leaving behind a universe composed only of photons and neutrinos, with no ordinary matter to form stars, planets, or life. However, our universe is clearly dominated by matter. There are stars, galaxies, and people, and very little antimatter. This implies that there must have been a tiny, yet incredibly significant asymmetry in the early universe, favouring matter over antimatter. For every billion antiparticles, there was roughly 1,000,000,001 particles. This minuscule excess of matter, perhaps generated through processes like baryogenesis, which is still an active area of theoretical and experimental research, was what survived the annihilation epoch. As the universe continued to cool, the remaining particles and antiparticles annihilated each other, with a tiny surplus of matter, particles being the only survivors. This surviving matter is what makes up everything we see today. After the formation of protons and neutrons, and the general annihilation of antimatter, the universe continued to cool. Electrons, being much less massive than protons and neutrons, could still be readily created and annihilated by photons for a longer period. It wasn't until the universe was about 1 second old that the temperature dropped below the threshold for creating electron-positron pairs. At this point, most electrons and positrons annihilated, leaving behind a residual population of electrons, balancing the positive charge of the protons. Neutrinos, which are very light and interact only via the weak nuclear force, also decoupled from the rest of the matter and radiation around this time, forming a cosmic neutrino background that is difficult to detect but is another relic of this hot, dense epoch. So, by approximately 1 second after the Big Bang, the particle soup had largely resolved into its more familiar constituents. The universe was still a very hot, dense plasma, but it was now primarily composed of protons, neutrons, electrons, and photons, along with a vast number of neutrinos. These were the raw ingredients for the next stages of cosmic evolution, including Big Bang nucleosynthesis, where protons and neutrons would fuse to form the first light atomic nuclei, paving the way for the later formation of atoms, stars, and galaxies. The transformation from pure energy to this initial particle content was a fundamental step in shaping the universe we inhabit. The universe around us is governed by 4 fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These forces dictate how particles interact, how atoms form, how stars shine, and how galaxies cluster together. At first glance, these forces appear distinct, operating in different ways and at vastly different strengths and ranges. However, a cornerstone of modern physics, particularly the study of the very early universe, is the idea of unification. that these seemingly distinct forces were once, under conditions of extreme energy and temperature, unified as a single fundamental force. As the universe expanded and cooled from its initial hot state, this unified force broke into the separate forces we observe today. Let us first briefly describe each of these four forces as they appear in our present-day, relatively cool universe. Gravity. This is the force of attraction between any two objects with mass or energy. It is the weakest of the four forces but has an infinite range. It governs the motion of planets around stars, the formation of stars and galaxies, and the large-scale structure of the entire universe. Electromagnetism. This force governs the interactions between electrically charged particles. It is responsible for all chemical reactions, the behavior of light, electricity, and magnetism. It holds electrons in orbit around atomic nuclei, forming atoms and molecules. Like gravity, it has an infinite range, but its strength is vastly greater than gravity. Strong nuclear force. This is the strongest of the four forces, but it acts only over incredibly short distances, typically within the nucleus of an atom. It is responsible for binding quarks together to form protons and neutrons, and for holding these protons and neutrons together within atomic nuclei. Without the strong force, atomic nuclei would fly apart due to the electromagnetic repulsion between positively charged protons. Weak nuclear force. This force is responsible for certain types of radioactive decay, such as beta decay, where a neutron transforms into a proton, or vice versa. It plays a crucial role in nuclear fusion processes in stars, including our Sun, but it has a very short range, even shorter than the strong force, and is significantly weaker than the strong and electromagnetic forces. The concept of force unification is not new to physics. A major triumph in the 19th century was James Clerk Maxwell's unification of electricity and magnetism into a single theory of electromagnetism. Before Maxwell, electricity and magnetism were considered separate phenomena, but he showed they were two different manifestations of the same underlying force, with light itself being an electromagnetic wave. Building on Maxwell's success, physicists in the 20th century began to wonder if the other forces could also be unified. The first major step beyond electromagnetism came in the 1960s and 70s with the electroweak unification. Sheldon Glashow, Abdus Salam, and Steven Weinberg independently developed a theory that showed that at very high energies, the electromagnetic force and the weak nuclear force are not separate, but are two aspects of a single electroweak force. This unification was a monumental achievement, as it demonstrated that forces could indeed merge under specific conditions. This theory predicted the existence of new force-carrying particles, the W and Z bosons, which were later experimentally discovered at the European Organisation for Nuclear Research, or CERN, in the 1980s, providing strong confirmation of the electroweak theory. The energies required for electroweak unification correspond to temperatures that existed in the universe when it was only about 10 to the power of minus 12 seconds old, or 1/trillionth of a second after the Big Bang. At this incredibly hot stage, particles interacted via the unified electroweak force. As the universe cooled below this critical temperature, the electroweak force broke into the distinct electromagnetic and weak forces we observe today. The next ambitious step in unification is the development of grand unification theories, or GUTS. These speculative theories aim to unify the electroweak force with the strong nuclear force. If a GUT is correct, then at even higher energies, corresponding to temperatures found when the universe was perhaps 10 to the power of minus 36 seconds old, these three forces, electromagnetic, weak, and strong, would have been unified into a single, grand unified force. At these energies, the universe would have been too hot for individual protons and neutrons to form, existing instead as a quark-gluon plasma. As the universe cooled through this epoch, the grand unified force would have broken down, first separating the strong force from the electroweak force, and then the electroweak force further splitting into the electromagnetic and weak forces. GUTS makes several predictions, such as proton decay and the existence of magnetic monopoles, none of which have been definitively observed yet, which means that either these theories are incorrect, or the phenomena occur at rates too rare for us to detect with current technology. The ultimate goal for physicists is to achieve a theory of everything, or TOEU, which would unify all four fundamental forces, including gravity, into a single, comprehensive framework. Such a unification is thought to have occurred at the very highest energies, corresponding to the Planck epoch, which existed up to approximately 10 to the power of minus 43 seconds after the Big Bang. At these unimaginably high temperatures, 10 to the power of 32 Kelvin, gravity would have been as strong as the other forces and unified with them. Developing a theory that successfully integrates gravity with quantum mechanics, which describes the other three forces, is one of the most significant unsolved problems in physics. Theories like string theory and loop quantum gravity are leading candidates for such a quantum theory of gravity and a potential theory of everything. The early universe serves as the only natural laboratory where such extreme energies and temperatures existed, allowing for these force unifications to occur. By studying the remnants of the Big Bang, such as the cosmic microwave background, and by probing high-energy interactions in particle accelerators, scientists hope to find clues that will lead to a complete understanding of how these fundamental forces were unified in the universe's first moments, and how they subsequently separated to shape the physical laws that govern our cosmos today. The idea of forces uniting in the hot, dense early universe is a powerful concept that underscores the deep interconnectedness of physical reality. As the universe continued its rapid expansion after the Big Bang, its temperature steadily decreased. This cooling was essential for the formation of the first stable atomic nuclei and, later, the first complete neutral atoms. This process occurred in two distinct phases. First, the creation of light atomic nuclei during Big Bang nucleosynthesis, and then, much later, the formation of neutral atoms during recombination. Big Bang nucleosynthesis, or BBN, began when the universe was only about 3 minutes and 46 seconds old. Before this time, the universe was too hot, with temperatures exceeding billions of Kelvin for atomic nuclei to hold together. Instead, it was a dense plasma of fundamental particles, primarily protons, neutrons, electrons, positrons, and a vast sea of energetic photons. Protons and neutrons could interconvert, but as the universe cooled, the conversion of neutrons into protons became less favourable, leading to a slight excess of protons. For every 7 protons, there was approximately 1 neutron. This precise ratio was critical for what was to follow. The initial hurdle for nucleosynthesis was the deuterium bottleneck. Deuterium, an isotope of hydrogen containing 1 proton and 1 neutron, is the simplest compound nucleus and the essential stepping stone for building heavier elements. However, at temperatures above approximately 900 million Kelvin, the high-energy photons in the universe would immediately smash apart any newly formed deuterium nuclei. This meant that even though protons and neutrons were present, they could not combine to form stable nuclei until the universe cooled sufficiently. Once the temperature dropped below this critical threshold, around 3 minutes and 46 seconds after the Big Bang, deuterium nuclei could finally survive. This opened the floodgates for a rapid series of nuclear fusion reactions. Deuterium quickly combined with other protons and neutrons to form heavier isotopes. For example, a deuterium nucleus could fuse with another proton to form helium-3, which has 2 protons and 1 neutron. Helium-3 could then fuse with a neutron to form helium-4, which has 2 protons and 2 neutrons, or with another deuterium nucleus to form helium-4. Helium-4 is an exceptionally stable atomic nucleus, and the nuclear reactions during BBN were highly efficient at producing it. Because each helium-4 nucleus requires 2 protons and 2 neutrons, and neutrons were relatively scarce compared to protons, the 1:7 ratio, virtually all available neutrons were incorporated into helium-4 nuclei. The remaining protons, which constituted the vast majority of the baryonic matter, remained as individual hydrogen nuclei. This process continued for about 17 minutes, effectively ending around 20 minutes after the Big Bang, when the universe had expanded and cooled so much that the density and temperature were too low for further nuclear fusion to occur. The result of Big Bang nuclear synthesis was a universe composed of approximately 75% hydrogen and 25% helium-4 by mass, with only trace amounts of deuterium, helium-3 and lithium-7. No heavier elements like carbon, oxygen or iron were formed during this period. The universe simply did not remain hot and dense enough for a sufficient duration to build up these more complex nuclei. The conditions for forming elements beyond lithium require the extreme pressures and temperatures found only in the cores of stars, which would not form for hundreds of millions of years. The predicted abundances of these light elements are one of the strongest pieces of evidence supporting the Big Bang theory. Astronomers observe the cosmic abundances of hydrogen, helium, and lithium in the most pristine ancient regions of the universe, such as distant gas clouds and the oldest stars, which have not been significantly altered by later stellar processes. The measured proportions match the BBN predictions with remarkable accuracy. This agreement confirms that the universe was indeed hot and dense enough in its early stages for these specific nuclear reactions to occur, and that it expanded and cooled at a rate consistent with our current cosmological models. Furthermore, the precise values of these abundances are sensitive to the amount of ordinary matter, or baryonic matter, in the universe. The success of BBN in matching observations provides a strong constraint on the total amount of baryonic matter, indicating it makes up only about 4 to 5% of the universe's total mass energy content. While the nuclei of the first elements were formed within the first 20 minutes, the universe was still too hot for these nuclei to capture electrons and form complete neutral atoms. Free electrons still roamed independently, constantly scattering photons. This state persisted for a much longer period. The universe remained an opaque ionized plasma, much like the interior of a star, where light could not travel freely. The second crucial phase, known as recombination, occurred much later, approximately 380,000 years after the Big Bang. By this time, the universe had continued to expand significantly, and its temperature had dropped to about 3000 Kelvin, roughly the temperature of the surface of a cool star. At this critical temperature, the kinetic energy of the free electrons was low enough that they could be captured by the positively charged atomic nuclei, protons and helium nuclei, to form stable neutral atoms. The term recombination is a bit misleading, as it was the first time electrons and nuclei combined, not a recombination. As electrons combined with nuclei, the universe underwent a dramatic transformation. With electrons now bound within atoms, they were no longer free to scatter photons. The universe suddenly became transparent to light. The photons that had been trapped and constantly scattering within the opaque plasma were now free to travel across the cosmos without interruption. These photons, released at the moment of recombination, are what we detect today as the cosmic microwave background radiation. Its uniform distribution and specific temperature of 2.725 Kelvin are direct evidence of this event. The formation of these first neutral atoms, primarily hydrogen and helium, marked the end of the plasma era and the beginning of the dark ages of the universe. For the first time, matter was organized into stable, neutral structures. This transition was fundamental because it allowed light to travel freely, and it also set the stage for the next major phase of cosmic evolution: the gravitational collapse of this neutral gas to form the first stars and galaxies. Without the birth of these first atoms, the universe would have remained an undifferentiated plasma, incapable of forming the complex structures we observe today. Following the formation of the first neutral atoms during the epoch of recombination, the universe entered a period known as the Cosmic Dark Ages. This era, spanning from approximately 380,000 years after the Big Bang to roughly 300 million to 500 million years later, is characterized by the absence of light sources in the visible spectrum. While the universe was no longer an opaque plasma, it was a largely featureless expanse of neutral gas, primarily hydrogen and helium, with no stars or galaxies yet to illuminate it. The onset of the Dark Ages was marked by the decoupling of matter and radiation. Before recombination, photons were constantly interacting with free electrons, making the universe opaque. Once electrons combined with atomic nuclei to form neutral atoms, these photons were free to travel unimpeded. This moment, 380,000 years after the Big Bang, is when the cosmic microwave background (CMB) radiation was released. As the universe continued to expand, these CMB photons stretched to longer wavelengths and cooled. eventually becoming the faint microwave glow we detect today. During the Dark Ages, the CMB was the only significant source of radiation, and its temperature continued to drop, meaning it provided less and less light in the visible range. During this long stretch of cosmic history, the universe was indeed dark. There were no stars shining, no galaxies blazing with starlight. The gas was almost entirely neutral, meaning its atoms had their full complement of electrons. This neutral gas, predominantly hydrogen and helium, was distributed relatively uniformly throughout space. The small density fluctuations that were imprinted on the cosmic microwave background, originating from quantum fluctuations in the very early universe, were still present, but they were very subtle. The dominant force at play during the Dark Ages was gravity. While the gas was largely uniform, the tiny overdensities, or regions where the gas was slightly denser than average, began to slowly attract more matter due to their slightly stronger gravitational pull. This process of gravitational collapse was incredibly slow during the Dark Ages because the universe was still relatively smooth, and the gravitational forces were weak over the vast distances. An essential component influencing this gravitational collapse was dark matter. Dark matter is a mysterious substance that does not interact with light or other electromagnetic radiation, making it invisible to telescopes. However, it does interact gravitationally. Cosmological models suggest that dark matter makes up about 27% of the universe's total mass energy content, far more than ordinary baryonic matter. During the Dark Ages, dark matter began to clump together under its own gravity, forming invisible structures known as dark matter halos. These halos acted as gravitational scaffolding, providing the initial gravitational wells into which the ordinary neutral gas could slowly fall. Without dark matter, the gravitational pull of ordinary matter alone would have been insufficient to form structures within the observed timescale of the universe. The temperature of the neutral gas during the Dark Ages continued to fall from the initial 3000 Kelvin at recombination. It eventually reached a minimum of around 10 Kelvin, or 10 degrees above absolute zero, after about 10 million to 100 million years. After this point, as the first structures began to form and contract, the gas within these collapsing regions would start to heat up again due to compression. The chemical composition of the universe during the Dark Ages was extremely simple. It consisted almost exclusively of hydrogen and helium, with only trace amounts of lithium. There were no heavier elements like carbon, oxygen, or iron, as these elements are forged in the interiors of stars and supernova explosions, which had not yet occurred. This lack of heavier elements meant that the cooling mechanisms for the gas were very limited. In the present-day universe, heavier elements act as efficient coolants, allowing gas clouds to radiate away energy and collapse more easily. In the Dark Ages, the primary coolant was molecular hydrogen, H2, which is less efficient than heavier elements. This limited cooling had implications for the properties of the first stars that would eventually form. Observing the Dark Ages directly is extremely challenging. Since there were no stars or galaxies emitting visible or ultraviolet light, conventional telescopes cannot see this period. However, scientists are exploring various indirect ways to probe this era. One promising avenue is through the detection of the 210 centimeter line of neutral hydrogen, also known as the hydrogen line, or spin-flip transition. This specific radio wavelength is emitted when the spin of the electron in a neutral hydrogen atom flips. By observing the redshifted 210 centimeter line from different points in the universe, astronomers hope to map the distribution of neutral hydrogen during the Dark Ages and study how the first structures began to emerge. Projects like the Low Frequency Array, or LOFAR, and the Square Kilometre Array, or SKA, are designed to detect these faint signals. The Dark Ages were a crucial transitional period. It was a time when the universe was literally dark, but beneath the quiet, expanding expanse, the seeds of future cosmic structures were slowly germinating. Gravity, guided by the distribution of dark matter, was patiently gathering the primordial gas into progressively denser clumps. This gradual accumulation of matter laid the groundwork for the universe's next major cosmic revolution, the ignition of the very first stars, which would end the Dark Ages and usher in the era of Ryanization and the formation of galaxies. Without this long, quiet period of gravitational growth, the universe would not have been able to build the complex cosmic tapestry we observe today. The Cosmic Dark Ages, a period of profound darkness lasting for hundreds of millions of years, eventually came to an end with the ignition of the very first stars. These pioneering celestial bodies, often referred to as population 3 stars, were fundamentally different from the stars we see in the night sky today. Their formation marked a pivotal moment in cosmic history as they began the process of illuminating the universe, forging the first heavy elements, and setting the stage for the formation of galaxies. The birth of these first stars was a direct consequence of the gravitational collapse that slowly unfolded during the Dark Ages. As discussed, the universe during this era was filled with a relatively uniform distribution of neutral hydrogen and helium gas, along with the invisible scaffolding of dark matter halos. These dark matter halos, formed by the gravitational clumping of dark matter, created gravitational potential wells into which the ordinary baryonic gas could slowly fall. Within these dark matter halos, regions of slightly higher gas density began to attract more and more surrounding gas. As the gas accumulated, its density increased, and the gravitational pull became stronger, leading to a runaway collapse. However, the process was not as straightforward as in the modern universe. The primordial gas consisted almost entirely of hydrogen and helium, with only trace amounts of lithium. Crucially, there were no heavier elements, which astronomers refer to as metals. In the modern universe, metals play a vital role in cooling gas clouds, allowing them to fragment into smaller, denser clumps that can form stars of various sizes. Without these efficient coolants, the primordial gas had fewer ways to radiate away the heat generated by gravitational compression. The primary cooling mechanism available to the primordial gas was the formation and excitation of molecular hydrogen, or H2. Hydrogen atoms could combine to form H2 molecules, which could then radiate energy away, allowing the gas cloud to cool and contract further. However, H2 is not a very efficient coolant compared to metals. This limited cooling meant that the gas clouds had to be much more massive before they could collapse sufficiently to form stars. As a result, the first stars are predicted to have been extraordinarily massive. Theoretical models suggest that population 3 stars typically had masses ranging from tens to hundreds, or even thousands of times the mass of our Sun. Some models even propose that the very first stars could have been as massive as 100,000 solar masses. This immense mass had profound implications for their characteristics and lifespans. Because of their enormous mass, population 3 stars were incredibly hot and luminous. Their cores reached extreme temperatures and pressures, causing nuclear fusion reactions to proceed at a furious rate. They burned through their hydrogen fuel much more quickly than smaller stars. Consequently, their lifespans were incredibly short, lasting only a few million years, compared to the billions of years our Sun is expected to live. The death of these massive first stars was as dramatic as their birth. They ended their lives in spectacular supernova explosions. These were not just any supernova. They were likely a specific type known as pair instability supernova for the most massive ones. In such an explosion, the star completely disintegrates, leaving no remnant behind. These first supernovae were crucial because they were the universe's first cosmic factories for heavier elements. Inside the cores of these massive stars, nuclear fusion had forged elements up to iron. The supernova explosions then dispersed these newly created heavier elements, such as carbon, oxygen, nitrogen, and silicon, into the surrounding intergalactic medium. This chemical enrichment was essential, as these metals would later become the building blocks for subsequent generations of stars, planets, and eventually life. The supernovae of the first stars also had another profound impact. They contributed to the reionization of the universe. After recombination, the universe was filled with neutral hydrogen and helium. The ultraviolet light emitted by the first stars was energetic enough to strip electrons from these neutral atoms, reionizing the intergalactic medium. This process was gradual, starting in localized bubbles around the first stars and galaxies, and eventually spreading throughout the cosmos. By about 1 billion years after the Big Bang, the universe was largely reionized, making it transparent to ultraviolet light once again. This reionization epoch is another critical phase in cosmic evolution, and its timing and progression are actively studied using observations of distant quasars and the cosmic microwave background. Directly observing population 3 stars is extremely challenging because of their short lifespans and the vast distances involved. They existed billions of years ago, and their light is incredibly faint and redshifted. Current telescopes, even the most powerful ones like the James Webb Space Telescope, are pushing the limits to detect the faint light from the very first galaxies which would contain these stars. While individual population 3 stars have not yet been definitively observed, their existence is inferred from the properties of the cosmic microwave background, the observed abundances of light elements, and the presence of heavier elements in later generations of stars. The chemical composition of the oldest stars we can observe today, known as population 2 stars, shows very low abundances of metals, consistent with them having formed from gas that was only slightly enriched by the supernovae of population 3 stars. The first stars were cosmic pioneers. They ended the long darkness, initiated the chemical enrichment of the universe, and began the process of reionization. Their short, violent lives set in motion a chain of events that led to the formation of the galaxies, stars, and planets we see today, ultimately making the universe a more complex and hospitable place. The formation of the first galaxies represents a crucial stage in the evolution of the universe, transforming a relatively smooth, dark expanse of gas into the complex, luminous structures we observe today. This process, which began hundreds of millions of years after the Big Bang, was driven primarily by gravity, with a pivotal role played by the mysterious substance known as dark matter. The standard cosmological model, often referred to as lambda CDM, lambda for dark energy and cold dark matter, provides the framework for understanding how these structures emerged through a hierarchical process, where smaller clumps of matter merged and grew into larger ones. The seeds of galaxy formation were sown much earlier, during the epoch of cosmic inflation, when tiny quantum fluctuations in the very early universe were stretched to macroscopic scales. These fluctuations manifested as minute variations in the density of matter and energy, imprinted on the cosmic microwave background. During the subsequent Dark Ages, as the universe expanded and cooled, these slight overdensities began to exert a stronger gravitational pull on surrounding matter. Crucially, the vast majority of the matter in the universe is not the ordinary baryonic matter, protons, neutrons, electrons, that makes up stars and galaxies, but rather dark matter. Dark matter, which accounts for about 27% of the universe's mass-energy content, does not interact with light or other electromagnetic radiation, making it invisible to telescopes. However, it does interact gravitationally. Because dark matter does not experience the electromagnetic forces that would cause ordinary gas to exert pressure and resist collapse, it was able to clump together much earlier and more efficiently than ordinary matter. During the Dark Ages, dark matter began to coalesce under its own gravity, forming invisible structures known as dark matter halos. These halos were the first large-scale structures to emerge in the universe. They varied in size, from small clumps with masses equivalent to 1 million suns to much larger ones. These dark matter halos acted as gravitational scaffolding, creating the potential wells into which the ordinary baryonic gas, primarily hydrogen and helium, could slowly fall. The process of gas accumulating within these dark matter halos was gradual. As the neutral gas fell into the gravitational embrace of a dark matter halo, it became compressed and heated. For stars to form, this gas needed to cool down so that it could become dense enough to collapse further. In the early universe, without the presence of heavier elements, which act as efficient coolants in modern gas clouds, the primary cooling mechanism for the primordial gas was the formation and excitation of molecular hydrogen, H2. This limited cooling meant that the gas clouds had to be quite massive before they could cool sufficiently to initiate star formation. The very first stars, known as population 3 stars, formed within these early, relatively small dark matter halos. These stars were typically much more massive than our Sun, burning through their fuel rapidly and ending their lives in spectacular supernova explosions within just a few million years. These supernovae were vital as they dispersed the first heavy elements, forged in the star's cores, into the surrounding gas. This chemical enrichment was a critical step, as these newly synthesized metals would later enable more efficient cooling in subsequent generations of gas clouds, allowing for the formation of smaller, more diverse stars. The earliest galaxies were not the grand spiral or elliptical structures we see today. Instead, they were likely much smaller, irregular clumps of stars and gas, forming within the most massive and densest of the early dark matter halos. These nascent galaxies, sometimes referred to as proto-galaxies or mini-halos, were the building blocks of larger galaxies. The process of galaxy formation is thought to be hierarchical, meaning that small structures formed first and then merged over cosmic time to create progressively larger ones. As the universe continued to evolve, these early mini-halos and proto-galaxies, still embedded within their dark matter halos, began to attract each other through gravity. They collided and merged, a process that was particularly frequent in the early universe when structures were closer together. These mergers were violent events, disrupting existing stellar orbits, triggering bursts of star formation, and leading to the growth of larger, more complex galaxies. Each merger brought in more gas, more stars, and more dark matter, contributing to the overall growth of the galactic structures. The role of dark matter in this hierarchical formation is paramount. Without its gravitational influence, ordinary matter alone would not have been able to clump together quickly enough to form the observed large-scale structures in the universe. The pressure exerted by the hot gas in the early universe would have prevented it from collapsing into structures on the scales of galaxies. Dark matter, by providing the initial gravitational scaffolding without being affected by pressure or electromagnetic forces, allowed the first structures to form, which then served as the gravitational anchors for ordinary matter. Observations from powerful telescopes like the Hubble Space Telescope and, more recently, the James Webb Space Telescope provide direct evidence for this hierarchical formation. These telescopes can peer deep into the universe, allowing astronomers to observe galaxies as they appeared billions of years ago, when the universe was much younger. They reveal numerous small, irregular, and often interacting galaxies in the early universe, which are consistent with the idea that larger galaxies formed through the mergers of smaller ones. The most distant galaxies observed are often small and appear to be actively forming stars, indicating they are in their early stages of development. Over billions of years, this process of gravitational collapse and hierarchical merging continued. Smaller galaxies merged to form larger ones, and these larger galaxies then grouped together to form galaxy clusters and superclusters, creating the vast cosmic web of filaments and voids that spans the universe today. The dark matter halos continued to grow, encompassing these larger structures. The properties of galaxies, such as their shape, size, and star formation rates, are influenced by their environment and their merger history. For example, elliptical galaxies are thought to be the result of multiple major mergers, while spiral galaxies may have experienced fewer significant merger events. In essence, galaxy beginnings were not a singular event but a continuous process driven by gravity and dark matter. From the initial quantum fluctuations, dark matter provided the gravitational framework for the first halos. Within these halos, primordial gas cooled and collapsed to form the first massive stars. The supernovae of these stars enriched the universe with heavier elements. Subsequently, these early small stellar systems and their dark matter halos merged repeatedly, building up the larger, more diverse galaxies that populate the universe today, a process that continues even in the present epoch. To understand our place in the vastness of the universe, it is helpful to consider our cosmic address, a hierarchical description that places our home planet within progressively larger structures, from our immediate neighborhood to the observable limits of the cosmos. This journey through scale provides a profound sense of perspective on the immense distances and structures that comprise the universe. Our journey begins on Earth, a rocky planet orbiting a star. Earth is the third planet from the Sun, a yellow dwarf star. The Sun, along with its 8 planets, numerous dwarf planets, asteroids, comets, and other celestial bodies, forms our solar system. The solar system is a relatively small, gravitationally bound system located in one of the spiral arms of a much larger structure. The solar system resides within the Milky Way galaxy. The Milky Way is a barred spiral galaxy, a vast collection of hundreds of billions of stars along with gas, dust and dark matter, all bound together by gravity. Our Sun is located in the Orion Arm, one of the smaller spiral arms of the Milky Way, approximately 27,000 light-years from the galactic centre. To give a sense of scale, the Milky Way galaxy is estimated to be about 100,000 light-years in diameter and approximately 1,000 light-years thick. The Sun orbits the galactic centre once every 230 million years, a period known as a cosmic year. From our vantage point within the disk, we see the collective light of billions of stars as a hazy band across the night sky, which is why it is called the Milky Way. The Milky Way galaxy is not alone in the universe. It is part of a small cluster of galaxies known as the Local Group. The Local Group is a gravitationally bound collection of over 50 galaxies, though most of these are dwarf galaxies. The two largest and most dominant members of the Local Group are the Milky Way and the Andromeda Galaxy. The Andromeda Galaxy, a large spiral galaxy, is about 2.5 million light-years away and is on a collision course with the Milky Way, with a predicted merger occurring in about 4.5 billion years. Other notable members of the Local Group include the Triangulum Galaxy, the Large Magellanic Cloud, and the Small Magellanic Cloud, the latter two being satellite galaxies of the Milky Way. The Local Group itself spans approximately 10 million light-years across. The Local Group, in turn, is a small component of an even larger structure, a supercluster of galaxies. For many years, the Local Group was considered part of the Virgo supercluster, a massive collection of galaxy clusters centered on the Virgo cluster, which is about 54 million light-years away. The Virgo supercluster contains thousands of galaxies and spans roughly 110 million light-years. Our Local Group is located near the edge of this supercluster, and we are gravitationally attracted towards its center. However, more recent and detailed mapping of the universe's large-scale structure has revealed that the Virgo supercluster is itself just a lobe of an even grander, more extensive supercluster, which has been named the Laniakea supercluster. The name Laniakea means immense heaven in Hawaiian. Discovered in 2014, the Laniakea supercluster is defined by the gravitational flow of galaxies towards a common center of mass, a region known as the Great Attractor. The Laniakea supercluster is truly enormous, containing approximately 100,000 galaxies and spanning about 500 million light-years across. Our Local Group is located near the edge of Laniakea, and we are, along with thousands of other galaxies, slowly being pulled towards the Great Attractor. Beyond the Laniakea supercluster, the universe continues to unfold into an intricate web-like pattern of galaxy clusters, superclusters, and vast, nearly empty regions called voids. This large-scale structure is often referred to as the cosmic web. Galaxies and clusters are concentrated along filaments, which are like cosmic threads, while between these filaments lie immense voids where galaxies are scarce. This cosmic web is the largest known structure in the universe, stretching for billions of light-years. The largest structure we can observe is the observable universe itself. This is not the entire universe, which may be infinite in extent, but rather the portion of the universe from which light has had enough time to reach us since the Big Bang. Because the universe is approximately 13.8 billion years old, and light travels at a finite speed, the maximum distance from which we can receive light is about 13.8 billion light-years in any direction. However, due to the ongoing expansion of the universe, the actual distance to the most distant objects whose light we are now receiving is much greater, estimated to be around 46.5 billion light-years in every direction from us. This means the diameter of the observable universe is approximately 93 billion light-years. Within this immense observable universe, there are estimated to be hundreds of billions, possibly even trillions of galaxies, each containing hundreds of billions of stars. Each of these stars may host its own system of planets. The sheer scale is almost incomprehensible. Our Earth is a tiny speck of dust orbiting an average star, which is one of hundreds of billions of stars in a galaxy that is one of dozens in a small group, which is part of a larger supercluster, itself embedded within the vast cosmic web that fills the observable universe. Understanding our cosmic address provides a crucial perspective. It highlights that we are not at the centre of the universe, nor are we particularly special in a cosmic sense. Our existence is part of a grand narrative of cosmic evolution, from the Big Bang to the formation of stars, galaxies, and ultimately complex life. This hierarchical view of the cosmos underscores the vastness and complexity of the universe, reminding us of the ongoing scientific quest to explore and understand our place within it. The Big Bang Theory provides a highly successful framework for understanding the evolution of our universe from an incredibly hot, dense state to its current vast and complex form. It explains the expansion of space, the cosmic microwave background radiation, and the abundance of light elements with remarkable accuracy. However, despite its triumphs, the Big Bang Theory, in its current form, encounters a fundamental limitation when attempting to describe the very first instant of the universe, the concept of a singularity. This edge of knowing represents a boundary beyond which our current laws of physics, particularly general relativity, break down, leaving crucial questions about the universe's ultimate origin unanswered. A singularity, in the context of general relativity, is a point where the density of matter and the curvature of space-time become infinite. According to the standard Big Bang model, if we extrapolate the universe's expansion backward in time, all matter and energy would converge to an infinitely dense point at time zero. This is often referred to as the initial singularity. While mathematically convenient, an infinite density and infinite curvature are problematic for physics. Infinities generally signal that a theory is incomplete or being applied beyond its valid domain. When general relativity predicts a singularity, it essentially tells us that it can no longer describe what is happening at that point. It is a mathematical breakdown, not necessarily a physical description of reality. One of the key figures in understanding this limitation was Stephen Hawking, who, along with Roger Penrose, developed the singularity theorems in the 1960s and 70s. These theorems demonstrated that, under very general conditions, assuming general relativity is correct and that the universe contains a reasonable amount of matter and energy, an initial singularity is an unavoidable consequence of the universe's observed expansion. This means that if we trace the universe back far enough, we inevitably arrive at a point where the density and curvature of space-time become infinite, and the concept of space and time, as we understand them, ceases to exist. The problem with the singularity is that it prevents us from asking what happened before, or what caused it. If all of space and time originated from this singular point, then the very concept of before becomes meaningless within the framework of general relativity. The theory simply cannot provide answers to these questions because its equations no longer apply. It is like trying to use a map that only shows roads to describe the ocean. It is the wrong tool for the job. The breakdown of general relativity at the singularity points to the need for a more comprehensive theory, one that can seamlessly integrate gravity with quantum mechanics. General relativity is a classical theory, meaning it describes gravity on large scales, but it does not account for the quantum nature of reality at extremely small scales. Quantum mechanics, on the other hand, describes the behavior of particles and forces at the atomic and subatomic level, where uncertainties and probabilities dominate. At the Planck scale, which is an unimaginably tiny length, about 10 to the power of minus 35 meters, and time, about 10 to the power of minus 43 seconds, quantum effects of gravity are expected to become dominant. The initial singularity of the Big Bang occurs precisely at this Planck scale, where both general relativity and quantum mechanics are simultaneously relevant, and neither theory alone is sufficient. This is where the quest for a theory of quantum gravity becomes paramount. Such a theory would aim to unify general relativity with quantum mechanics, providing a consistent description of gravity at extremely small scales and high energies. Leading candidates for a theory of quantum gravity include string theory and loop quantum gravity. These theories offer potential ways to resolve the singularity problem. String theory, for instance, proposes that fundamental particles are not point-like, but are instead tiny, vibrating one-dimensional strings. At the Planck scale, these strings would smear out the singularity, preventing infinite densities from arising. In some string theory models, the Big Bang might not be the absolute beginning, but rather a transition from a previous state, perhaps a collision of higher dimensional branes. This could potentially eliminate the singularity by replacing it with a finite, albeit extreme event. Loop quantum gravity, another approach, suggests that space-time itself is not continuous, but is granular, made up of discrete loops, or atoms of space-time at the Planck scale. In this framework, the singularity might be replaced by a big bounce, where the universe contracts to a minimum but finite size before rebounding into expansion, avoiding infinite density. This would imply that our universe is part of a cyclic process, with no true beginning or end. The edge of knowing also extends to the very early universe before the electroweak epoch, particularly the period of cosmic inflation. While inflation theory successfully addresses several puzzles of the standard Big Bang model, such as the flatness and horizon problems, it does not explain what caused inflation itself or what existed before it. Inflationary models typically require an inflaton field to drive the exponential expansion, but the precise nature of this field and its initial conditions are still unknown. Some inflationary scenarios, particularly chaotic inflation, suggest that inflation might be eternal, leading to a multiverse where new universes are constantly being spawned. If this is the case, then our Big Bang is just one event in a much larger, eternally inflating cosmos, pushing the ultimate origin question to a higher level of complexity. Furthermore, the edge of knowing encompasses the fundamental constants of nature. The values of these constants, such as the strength of gravity, the mass of an electron, or the speed of light, appear to be finely tuned for the existence of stars, galaxies, and life. If these constants were even slightly different, the universe might be radically different or incapable of supporting complex structures. The Big Bang theory does not explain why these constants have their particular values. Some physicists appeal to the anthropic principle or the multiverse concept to address this, suggesting that we simply find ourselves in a universe where these values are suitable for our existence, and other universes might have different values. However, these are philosophical arguments rather than direct scientific explanations derived from a fundamental theory. In essence, the initial singularity of the Big Bang represents a boundary for our current physical theories. It is the point where general relativity, our best description of gravity on large scales, breaks down. Overcoming this limitation requires a quantum theory of gravity, which is one of the most challenging and active areas of research in theoretical physics. Until such a theory is developed and experimentally verified, the very first instant of the universe will remain shrouded in mystery, an ultimate edge of knowing that continues to inspire scientific inquiry. The question, what caused the Big Bang, naturally leads to an even more profound and challenging inquiry. What was there before the Big Bang? This question, however, immediately confronts a fundamental conceptual hurdle. The notion that time itself, as we understand it, may have begun with the Big Bang. If time originated with the universe's expansion, then the concept of before becomes meaningless in a physical sense, posing a significant challenge to both scientific and philosophical thought. In the framework of general relativity, space and time are not separate, fixed entities, but are interwoven into a single fabric called space-time. This fabric is dynamic, capable of being stretched, warped, and curved by the presence of mass and energy. The Big Bang theory describes the evolution of this space-time fabric from an initial, extremely dense and hot state. According to the standard model, if we trace the expansion of the universe backward in time, we arrive at a point where space-time itself collapses to an infinitely dense singularity. At this singularity, not only does matter become infinitely compressed, but the very fabric of space-time ceases to exist in a meaningful way. If space-time itself began at the Big Bang singularity, then there was no before in the temporal sense. Time, as a dimension along which events unfold, would have emerged with the universe. This is a difficult concept to grasp because our human experience is deeply rooted in a linear progression of time, where every event has a preceding cause. We intuitively think of a beginning as something that must have been preceded by something else. However, if time itself is a property of the universe, and the universe began at the Big Bang, then asking what happened before is akin to asking what is north of the North Pole. The question loses its meaning within the defined coordinate system. This idea was famously articulated by Stephen Hawking, who suggested that asking what happened before the Big Bang is like asking what is south of the South Pole. There is nothing south of the South Pole because the concept of south breaks down at that point on the globe. Similarly, the concept of before breaks down at the Big Bang singularity. This perspective implies that the universe, along with time, simply came into existence at that point, and there is no prior physical state or temporal dimension to discuss. However, this interpretation is based on general relativity, which, as discussed, breaks down at the singularity. The search for a quantum theory of gravity aims to resolve this breakdown and might offer alternative perspectives on the nature of time at the very earliest moments. If a quantum theory of gravity eliminates the singularity, replacing it with a finite albeit extreme state, then the concept of before might regain some physical meaning, though perhaps not in the conventional sense. One theoretical possibility that addresses time before time is the Big Bounce hypothesis. This idea, often explored within the framework of loop quantum gravity, suggests that the Big Bang was not the ultimate beginning, but rather a rebound from a previous contracting universe. In this cyclic model, the universe undergoes an endless series of expansions and contractions. A previous universe would have contracted to an extremely dense but finite state, avoiding the singularity, then bounced back into expansion, leading to our current Big Bang. If the Big Bounce is correct, then there was indeed a before, a previous cosmic cycle, and time would have existed continuously through the bounce, albeit in a highly compressed and extreme form. This model offers a way to avoid the problem of an absolute beginning of time. Another approach comes from certain models within string theory and M theory, which propose higher dimensions and the existence of branes, multi-dimensional membranes. In some brane cosmology scenarios, our universe is a three-dimensional brane existing within a higher dimensional space. The Big Bang, in this context, could be the result of a collision between two such branes, or a brane emerging from a higher dimensional bulk. In these models, time might exist in the higher dimensional space even before the brane collision that created our universe. This would mean that before our Big Bang, there was a different kind of reality, operating in higher dimensions, with its own temporal progression. The concept of an eternal inflation also touches upon the idea of time before time. In some inflationary models, inflation, once it starts, never truly ends everywhere. Instead, it continues indefinitely in some regions, constantly spawning new bubble universes within a vast, ever-inflating multiverse. In this scenario, our Big Bang would be just one such bubble universe emerging from a larger, eternally inflating background. Time in the larger multiverse could be continuous, with our universe's beginning being a local event within that larger temporal framework. Philosophically, the idea of time having a beginning is deeply challenging. It forces us to reconsider our fundamental assumptions about causality and existence. If there was no time before the Big Bang, then the concept of a cause in the traditional sense becomes problematic. A cause typically precedes its effect in time. If there is no time, there can be no temporal precedence. This leads to questions about whether the universe caused itself, or if the concept of causation needs to be redefined for the very origin of existence. Ultimately, the question of time before time remains one of the most profound and unanswered questions in cosmology and philosophy. Our current scientific models, primarily general relativity, suggest a beginning of time at the Big Bang singularity. However, the limitations of these models at extreme conditions motivate the search for a quantum theory of gravity, which might offer new insights such as a Big Bounce or a higher dimensional reality, where time could have a more continuous existence. Until such a theory is developed and confirmed, the nature of time at the universe's origin will continue to be a subject of intense speculation and research. Quantum mechanics is a fundamental theory in physics that describes the behavior of matter and energy at the smallest scales, particularly at the level of atoms and subatomic particles. Unlike classical physics, which describes the world in terms of definite positions and momenta, quantum mechanics introduces concepts that are often counterintuitive and probabilistic. Understanding its basic principles is crucial for comprehending the conditions of the very early universe, where quantum effects were dominant and profoundly shaped the cosmos. One of the core principles of quantum mechanics is quantization. This means that certain physical quantities, such as energy, angular momentum, and electric charge, do not exist in continuous values but rather in discrete packets, or quanta. For example, an electron in an atom can only occupy specific energy levels. It cannot exist at any energy in between. When an electron moves from one energy level to another, it absorbs or emits a specific quantum of energy, typically in the form of a photon. This concept was first introduced by Max Planck at the turn of the 20th century to explain blackbody radiation, and it revolutionized physics. Another fundamental concept is wave-particle duality. Quantum mechanics posits that particles, such as electrons and photons, can exhibit properties of both waves and particles. For instance, light can behave as a wave, demonstrating phenomena like diffraction and interference, but it can also behave as a particle, photon, carrying discrete packets of energy. Similarly, electrons, which we typically think of as particles, can also exhibit wave-like behavior, as shown in electron diffraction experiments. This duality means that the traditional distinction between waves and particles breaks down at the quantum level. The Heisenberg uncertainty principle is a cornerstone of quantum mechanics. Formulated by Werner Heisenberg, it states that there are fundamental limits to the precision with which certain pairs of physical properties of a particle, such as its position and momentum, can be known simultaneously. The more precisely you measure one property, the less precisely you can know the other. This is not a limitation of our measuring instruments, but an inherent property of nature at the quantum scale. For example, if you know an electron's exact position, its momentum becomes completely uncertain, and vice versa. This principle has profound implications for the vacuum itself. According to quantum mechanics, even seemingly empty space, or the quantum vacuum, is not truly empty. Instead, it is a hive of activity, constantly fluctuating with the spontaneous creation and annihilation of virtual particles. These particle-antiparticle pairs briefly pop into existence from the vacuum, exist for an incredibly short time, and then disappear back into the vacuum, all in accordance with the uncertainty principle. While these virtual particles cannot be directly observed, their effects are measurable, for example, in the Casimir effect. This concept of a dynamic, fluctuating vacuum is highly relevant to the early universe. The probabilistic nature of quantum mechanics is another key departure from classical physics. Unlike classical physics, which predicts definite outcomes for events, quantum mechanics predicts the probabilities of various outcomes. For example, when an electron is in a superposition of states, a combination of multiple possible states simultaneously, we cannot know its exact state until it is measured. The act of measurement collapses the wave function, forcing the electron into a single definite state. This inherent randomness and the role of observation are central to the quantum world. The relevance of these quantum mysteries to the early universe is profound. In the very first moments after the Big Bang, the universe was incredibly small, dense, and hot. It was compressed to scales where quantum effects were not just relevant but absolutely dominant. The entire observable universe, which is now billions of light years across, originated from a region that was smaller than a subatomic particle. At these scales, the classical laws of physics, particularly general relativity, which describes gravity on large scales, break down. This is where the need for a quantum theory of gravity arises. To fully understand the Planck epoch, from time 0 to 10 to the power of minus 43 seconds, where all four fundamental forces were unified and quantum effects of gravity were significant, a theory that successfully combines quantum mechanics with general relativity is essential. Without it, we cannot fully describe the initial conditions of the universe or resolve the singularity problem. Theories like string theory and loop quantum gravity are attempts to achieve this unification. Furthermore, quantum mechanics plays a crucial role in the origin of structure in the universe, particularly through the theory of cosmic inflation. Inflation proposes that the universe underwent an extremely rapid, exponential expansion in its earliest moments. During this inflationary period, tiny microscopic quantum fluctuations in the energy field driving inflation, the inflaton field, were stretched to macroscopic scales. These quantum jitters, which are inherent uncertainties in the quantum vacuum, became the seeds of all the large-scale structures we see today. The slight overdensities caused by these stretched quantum fluctuations eventually grew, under gravity, into the galaxies, galaxy clusters, and the vast cosmic web. The observed pattern of temperature fluctuations in the cosmic microwave background radiation is remarkably consistent with the predictions of inflation, reinforcing the idea that quantum mechanics played a fundamental role in shaping the universe's structure. The matter-antimatter asymmetry, another puzzle of the early universe, may also find its explanation in quantum mechanics. While the precise mechanism is still unknown, theories of baryogenesis suggest that subtle quantum processes in the very early universe, perhaps involving interactions beyond the standard model of particle physics, led to a slight excess of matter over antimatter, allowing our matter-dominated universe to exist. In classical physics, a vacuum is understood as simply empty space, a region devoid of matter or energy. If one were to remove all particles, all radiation, and all fields from a given volume, what would remain, according to classical thought, is nothingness. However, the revolutionary insights of quantum mechanics radically altered this perception. In the quantum realm, the concept of a vacuum is profoundly different. It is not truly empty, but rather a dynamic, effervescent sea of fluctuating energy from which particles can momentarily emerge and vanish. This is the concept of the quantum vacuum. The fundamental principle underlying this vibrant nature of empty space is the Heisenberg uncertainty principle, a cornerstone of quantum mechanics. This principle, formulated by Werner Heisenberg, states that there are inherent limitations to the precision with which certain pairs of physical properties of a particle can be simultaneously known. For example, one cannot precisely know both the position and the momentum of a particle at the same time. Similarly, there is an uncertainty relationship between energy and time. This energy-time uncertainty means that for a very short duration, the energy of a system, even a vacuum, can fluctuate significantly from its average value. The shorter the time interval, the larger the possible energy fluctuation. These transient energy fluctuations in the quantum vacuum are sufficient to allow for the spontaneous creation of pairs of particles and their corresponding antiparticles. These are known as virtual particles. For an incredibly brief moment, a particle and its antiparticle, such as an electron and a positron, or a photon and an antiphoton, which is just another photon, can spontaneously pop into existence from the quantum vacuum, drawing energy from these temporary fluctuations. However, because energy must ultimately be conserved, these virtual particles must annihilate each other almost immediately, returning their borrowed energy back to the vacuum. The entire process occurs so quickly that these virtual particles typically cannot be directly observed or detected in the conventional sense. They are virtual precisely because they do not exist as stable, long-lived entities. The analogy often used to describe the quantum vacuum is that of a boiling or bubbling pot. While the pot may appear calm from a distance, up close, one sees incessant activity on the surface, with bubbles constantly forming, rising, and bursting. Similarly, the quantum vacuum, though appearing empty on macroscopic scales, is ceaselessly churning with the birth and death of these ephemeral virtual particle-antiparticle pairs. It is not a static void, but a roiling, energetic environment, even at its lowest possible energy state. Despite their fleeting nature, the existence of virtual particles in the dynamic quantum vacuum is not merely a theoretical curiosity. It has been confirmed by various experimental observations. One of the most famous pieces of evidence is the Casimir effect, first predicted by Dutch physicist Hendrik Casimir in 1948 and later experimentally verified. The Casimir effect describes a small attractive force that arises between two uncharged parallel conducting plates placed very close to each other in a vacuum. The explanation for this force lies in the quantum vacuum. Virtual particles with wavelengths too large to fit between the plates are excluded from that region, while virtual particles with smaller wavelengths can still exist there. This creates an imbalance in the pressure exerted by the virtual particles, resulting in a net attractive force that pushes the plates together. The precise magnitude of this force has been measured and matches theoretical predictions derived from the quantum vacuum. Another piece of evidence comes from the Lamb shift in atomic physics. The Lamb shift refers to a tiny but measurable difference in the energy levels of electrons in atoms, specifically between the two 20^1/2 and two 20p⁴ states of the hydrogen atom, which according to the Dirac equation, a relativistic quantum mechanical equation, should have identical energies. This minute energy shift is explained by the interaction of the electron with virtual photons continuously appearing and disappearing in the quantum vacuum. These virtual photons momentarily perturb the electron's energy levels, causing the observed shift. The experimental confirmation of the Lamb shift in 1947 provided a crucial validation of quantum electrodynamics, the quantum field theory of electromagnetism, and the reality of virtual particles. The concept of the quantum vacuum also plays a role in understanding Hawking radiation from black holes. Stephen Hawking theorized that black holes are not entirely black, but can emit thermal radiation. This phenomenon is explained by the behavior of virtual particle-antiparticle pairs near the black hole's event horizon. Sometimes, one particle of a virtual pair falls into the black hole while its partner escapes. The escaping particle effectively carries away energy from the black hole, causing it to slowly lose mass and eventually evaporate over immense timescales. This process highlights how the quantum vacuum's fluctuations can have macroscopic, observable consequences in extreme gravitational environments. The vacuum energy associated with these quantum fluctuations is a concept that also intersects with cosmology. In modern cosmological models, a form of vacuum energy is considered a candidate for dark energy, the mysterious force responsible for the accelerated expansion of the universe. If the quantum vacuum truly has a non-zero energy density, this energy would exert a repulsive gravitational force, acting like a cosmological constant. However, theoretical calculations of vacuum energy are vastly larger than the observed dark energy density, presenting a significant puzzle known as the cosmological constant problem. This discrepancy suggests that our understanding of vacuum energy or gravity at the quantum level is still incomplete. The concept that a universe, as vast and complex as our own, could theoretically emerge from nothing is one of the most provocative and challenging ideas in modern cosmology. This nothing, however, is not the intuitive philosophical void, but rather the quantum vacuum, a concept far removed from classical emptiness. The speculative idea that our universe could have arisen as a quantum fluctuation within this dynamic quantum vacuum pushes the boundaries of our scientific understanding and philosophical contemplation of origins. As established, the quantum vacuum is not truly empty. Instead, it is a restless, fluctuating field of energy, governed by the principles of quantum mechanics. Virtual particles constantly pop into and out of existence, borrowing energy for fleeting moments before annihilating. This incessant activity means that even in its lowest energy state, the quantum vacuum is never truly still. It possesses a fundamental inherent instability. It is this inherent instability and the principle of quantum fluctuation that form the basis for the idea of a universe emerging from what some physicists refer to as nothing, meaning a state devoid of classical matter, energy, space, and time, but not devoid of quantum potential. The conceptual leap involves considering whether an entire universe, with its immense energy and complexity, could itself be a giant quantum fluctuation. Normally, virtual particles are microscopic and short-lived due to the energy-time uncertainty principle. For a macroscopic structure like a universe to emerge, it would seem to require an enormous violation of energy conservation. However, some theoretical models propose a way around this. One key insight comes from considering the total energy of the universe. According to general relativity, energy in the universe includes not only the positive energy of matter and radiation, but also the negative energy associated with gravity. Gravitational energy is negative because gravity is an attractive force. As objects pull closer together, their gravitational potential energy decreases. In certain cosmological models, it is theoretically possible that the positive energy of all the matter and radiation in the universe could be precisely balanced by the negative gravitational potential energy. If this were the case, the total net energy of the universe would be exactly zero. A zero-energy universe is crucial for the universe from nothing hypothesis. If the total energy of the universe is zero, then its emergence from the quantum vacuum would not violate the fundamental principle of energy conservation. A quantum fluctuation of zero total energy could theoretically arise spontaneously from the vacuum without requiring an external energy source. This idea has been explored by physicists like Edward Tryon in the 1970s and later elaborated upon by Stephen Hawking and Lawrence Krauss. Hawking, in particular, emphasized that if the universe's total energy is zero, then the universe can and will create itself from nothing. The second crucial element that allows a microscopic quantum fluctuation to inflate into a macroscopic universe is cosmic inflation. If the universe did indeed emerge as an incredibly tiny quantum fluctuation, it would initially be microscopic, existing for an extremely short duration. However, if such a fluctuation contained within it the seeds of an inflaton field, a hypothetical field responsible for cosmic inflation, then this tiny region could undergo a period of incredibly rapid exponential expansion. This inflationary burst, lasting for only a tiny fraction of a second, would stretch the microscopic fluctuation to macroscopic, even cosmic scales, creating the vast, uniform and flat universe we observe today. Without inflation, a spontaneous quantum fluctuation would simply pop into and out of existence without ever growing into a persistent large-scale universe. This concept suggests that the universe did not need a pre-existing space or time to emerge into. Instead, space and time themselves would have been created as part of the quantum fluctuation. Before the fluctuation, there was no before in a temporal sense, and no where in a spatial sense, as those concepts emerge with the universe. It's a universe spontaneously tunneling into existence from the quantum vacuum, much like a particle tunneling through an energy barrier in quantum mechanics. This is often compared to the phenomenon of quantum tunneling, where a particle can pass through a barrier even if it does not have enough classical energy to do so, relying on the probabilistic nature of quantum mechanics. Physicists such as Alexander Vilenkin have further developed these ideas. Vilenkin's work, particularly his tunneling from nothing proposal, suggests that the universe could have quantum mechanically tunneled from a state of nothing, a state without classical space-time, into a state where inflation began. This would imply a spontaneous, uncaused emergence of the universe, rooted entirely in the laws of quantum physics. It is important to emphasize that the universe from nothing hypothesis is highly speculative and remains a subject of ongoing theoretical research and debate within the scientific community. It relies on extrapolating quantum mechanics to scales and conditions far beyond what can be directly tested in laboratories. Furthermore, the definition of nothing used in this context, the quantum vacuum, is itself a rich, energetic entity, not the absolute void that might be intuitively imagined. This leads to philosophical discussions about whether a quantum vacuum truly constitutes nothing. Critics argue that if the vacuum has properties and laws that govern it, then it is not truly nothing. Despite its speculative nature, the idea of a universe emerging from the quantum vacuum provides a potential scientific answer to the question of cosmic origins, operating entirely within the framework of known physical laws. It eliminates the need for a supernatural creator or a pre-existing cosmic state outside of physical laws. Instead, it suggests that the universe's existence might be a natural consequence of the fundamental principles of quantum mechanics, arising from the very fabric of reality itself. However, direct empirical evidence for such an event is currently beyond our reach, and many profound questions about the ultimate origin and nature of existence continue to remain open. Loop quantum gravity, often abbreviated as LQG, is a theoretical framework that attempts to unify two of the most successful but fundamentally incompatible theories in physics: Albert Einstein's general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which governs the behavior of matter and energy at the smallest subatomic scales. The primary goal of loop quantum gravity is to develop a quantum theory of gravity, resolving the singularity problem of the Big Bang and providing a consistent description of space-time at the most extreme conditions, such as those present in the very early universe or inside black holes. General relativity, published by Einstein in 1915, revolutionized our understanding of gravity by treating it not as a force acting at a distance, but as a manifestation of the curvature of space-time. Massive objects warp the fabric of space-time, and this curvature dictates how other objects move. This theory has been incredibly successful in describing phenomena from planetary orbits to the expansion of the universe. However, general relativity is a classical theory. It does not incorporate the probabilistic and quantized nature of reality at the quantum level. Quantum mechanics, developed throughout the 20th century, successfully describes the other three fundamental forces of nature: electromagnetism, the strong nuclear force, and the weak nuclear force, in terms of quantized particles and fields. It introduced revolutionary concepts such as wave-particle duality, the Heisenberg uncertainty principle, and the idea of a quantum vacuum. The problem arises when one tries to apply quantum mechanics to gravity. General relativity describes space-time as a smooth, continuous manifold, while quantum mechanics suggests that everything, including space-time itself, should be quantized or made of discrete units at sufficiently small scales. Attempts to simply quantize general relativity using standard quantum field theory techniques lead to infinities that cannot be removed, indicating a fundamental incompatibility. Loop quantum gravity approaches this problem by attempting to quantize spacetime directly, rather than quantizing a gravitational field within a pre-existing spacetime. The central idea of LQG is that space and time are not continuous as we perceive them, but are instead discrete, made up of tiny indivisible units, much like a fabric woven from tiny fundamental loops or atoms of spacetime. These loops are incredibly small, existing at the Planck scale, which is approximately 10 to the power of minus 35 meters. At our everyday macroscopic scales, these discrete units are imperceptible, and spacetime appears continuous and smooth, just as a finely woven cloth appears smooth from a distance. In LQG, the fundamental entities are not spacetime points, but rather quantum states of geometry. These states are described by spin networks, which are graphs where lines represent quantized loops of gravity, and nodes represent discrete units of volume. These spin networks evolve over time, forming spin foams that describe the quantum history of spacetime. This granular structure of spacetime has profound implications. It suggests that there is a minimum possible unit of length and a minimum possible unit of area and volume, meaning that space is truly atomized at its most fundamental level. One of the most significant implications of loop quantum gravity is its potential to resolve the singularity problem of the Big Bang. In general relativity, extrapolating the universe backward in time leads to an initial singularity, where density and spacetime curvature become infinite. This is where the theory breaks down. In LQG, because space itself is quantized and there is a minimum unit of volume, an infinite density becomes impossible. Instead, as one traces the universe backward, it reaches a state of maximum but finite density and curvature, where it then bounces back into expansion from a previous contracting phase. This concept is known as the Big Bounce. The Big Bounce hypothesis, emerging from LQG, suggests that our universe is not the first, but rather one in a potentially infinite series of universes, each undergoing cycles of expansion and contraction. In this scenario, the Big Bang is not an absolute beginning of time and space, but a transition point where a contracting universe rebounded into an expanding one. This offers a radical alternative to the initial singularity, providing a continuous, albeit extreme, timeline for the cosmos. It implies that before the Big Bang, there was a previous cosmic epoch, albeit one that was contracting. Loop quantum gravity also addresses the challenge of quantum mechanics at the event horizon of black holes. Just as it avoids the Big Bang singularity, LQG suggests that the singularity at the center of a black hole is also replaced by a quantum bounce. This implies that matter falling into a black hole might not be destroyed in a singularity, but could instead pass through a bounce into another region of space-time, or perhaps even another universe. It is important to note that loop quantum gravity is still a theoretical framework under development, and it has not yet been experimentally verified. The scales at which its effects would be noticeable, the Planck scale, are far beyond the reach of current particle accelerators or astronomical observations. However, LQG offers a mathematically rigorous and internally consistent approach to unifying gravity with quantum mechanics, It provides a compelling picture of a universe where space and time are not just backdrops for physical events, but are active, quantized participants in the cosmic drama, with profound implications for our understanding of the universe's ultimate origin and the nature of reality itself. Its predictions, particularly the Big Bounce, offer a fascinating alternative to the standard Big Bang singularity, pushing the boundaries of scientific inquiry into the most fundamental questions about existence. The standard Big Bang model describes the origin of our universe from an initial, infinitely dense and hot singularity. However, this singularity represents a point where the laws of physics, particularly Albert Einstein's theory of general relativity, break down. This breakdown has led physicists to explore alternative models that might provide a more complete and continuous description of cosmic history. One such compelling alternative is the Big Bounce theory, which proposes that our universe did not begin from a singularity but rather emerged from the collapse of a previous universe, rebounding from an extreme but finite state of compression. The Big Bounce hypothesis offers a solution to the singularity problem inherent in the Big Bang. Instead of an infinite density at time zero, the Big Bounce posits that the universe contracted to an incredibly dense but finite state, a point where quantum gravitational effects become dominant and prevent further collapse. At this point of maximum compression, the universe bounces and begins a new phase of expansion, leading to the universe we observe today. This implies that our universe is not the first, but part of an endless, or at least very long, cycle of expansion and contraction. The theoretical underpinnings for the Big Bounce largely come from the field of quantum gravity, specifically from loop quantum gravity, or LQG. General relativity, a classical theory, predicts the singularity. However, at the Planck scale, an unimaginably tiny length, approximately 10 to the power of minus 35 meters, and time, approximately 10 to the power of minus 43 seconds, quantum effects of gravity are expected to become dominant. Loop quantum gravity attempts to bridge the gap between general relativity and quantum mechanics by quantizing space-time itself, suggesting that space is made of discrete indivisible units rather than being continuous. Within the framework of loop quantum gravity, the singularity is avoided. As the universe contracts, the density and curvature of space-time increase. However, LQG predicts a strong repulsive force at extremely high densities, a quantum gravity effect that becomes significant when the universe approaches the Planck density. This repulsive force acts like a quantum pressure that prevents the universe from collapsing to an infinite density. Instead, it forces the contracting universe to rebound into a new phase of expansion. This mechanism is what gives the theory its name, the Big Bounce. This means that for a universe undergoing a Big Bounce, time does not have an absolute beginning. Instead, time would have existed continuously through the bounce. The universe would have undergone a period of contraction, reaching a minimum but non-zero size and finite maximum density, before transitioning seamlessly into a new phase of expansion. This offers a radical solution to the question of what was before the Big Bang. The answer would be a previous phase of cosmic contraction. The idea of a cyclic universe, which the Big Bounce naturally implies, has been considered by cosmologists for a long time. However, older cyclic models, often based purely on classical general relativity, face significant challenges, particularly the entropy problem. In a universe that repeatedly contracts into a big crunch and then re-expands from a new Big Bang, each cycle would accumulate entropy. Entropy, a measure of disorder or the unavailable energy in a system, always increases in a closed system according to the second law of thermodynamics. If entropy were to increase with each cycle, subsequent cycles would become progressively larger and longer, eventually leading to a cold, dilute, and infinitely expanded state, breaking the cycle. The quantum nature of the Big Bounce, however, might offer ways to circumvent this problem, though this remains an active area of research and debate within the scientific community. The Big Bounce model offers several intriguing implications for the observable universe. For example, it might provide a natural explanation for the flatness of the universe and the uniformity of the cosmic microwave background, CMB, without necessarily relying on cosmic inflation. In some Big Bounce scenarios, the preceding contracting phase could naturally smooth out initial anisotropies and flatten the universe, providing an alternative to the inflationary mechanism. Furthermore, the quantum fluctuations that would become the seeds of cosmic structure could arise from the quantum effects during the bounce itself, rather than solely from inflation. Observational evidence for the Big Bounce is currently indirect and highly sought after. Scientists are looking for specific signatures in the cosmic microwave background, which might retain subtle imprints from the pre-bounce era. One potential signature could be a distinct pattern of gravitational waves, different from those predicted by standard inflationary models. Gravitational waves are ripples in space-time, and if they were generated during the extreme conditions of the bounce, their unique characteristics could offer clues. Detecting and analysing these primordial gravitational waves is a major goal for future astronomical missions. Another area of investigation involves the specific distribution of density fluctuations in the universe. While inflation predicts a nearly scale-invariant spectrum of fluctuations, some Big Bounce models might predict slight deviations from this, particularly on very large scales, which could be discernible with future precision measurements of the CMB and large-scale structure surveys. It is important to emphasize that the Big Bounce theory remains a theoretical framework, still under active development and refinement. It is not yet as widely accepted as the standard inflationary Big Bang model, largely due to the lack of direct observational evidence that can definitively distinguish it from other cosmological models. However, its elegance in resolving the singularity problem and its potential to offer a complete, non-singular description of the universe's entire history make it a compelling and actively researched alternative in modern cosmology. It represents a significant departure from the idea of a singular beginning, proposing instead a universe that cycles through eternal phases of birth, death, and rebirth. The idea of a universe that undergoes repeated phases of expansion and contraction, an endless cosmic cycle, has a long history in cosmological thought, predating even the modern Big Bang theory. Such models, often referred to as cyclic or oscillatory universes, propose that our current phase of cosmic expansion is not a unique event, but merely one iteration in an eternal cosmic dance of birth, death, and rebirth. While historically challenged by fundamental physical problems, modern theoretical advances, particularly from quantum gravity and string theory, have led to renewed interest and sophisticated new versions of these cyclic scenarios. Classically, cyclic universe models often envisioned a big crunch scenario. In this view, the universe, after a period of expansion, would eventually exhaust its kinetic energy, and gravity would then pull all matter and energy back together. This contraction would culminate in a hot, dense state, a big crunch, which was often conceptually linked to the Big Bang as the starting point for a new expansion phase. The universe would then rebound from this crunch, effectively resetting itself for a new cycle. However, these classical cyclic models faced a significant theoretical hurdle known as the entropy problem. Entropy, a measure of disorder or the dispersal of energy, is always increasing in a closed system according to the second law of thermodynamics. If the universe were truly cyclical in the classical sense, each cycle would begin with a certain amount of entropy and end with a greater amount. This means that successive cycles would be progressively larger and longer, with higher total entropy, eventually leading to a state of perpetual expansion and increasing coldness, thus preventing a true return to initial conditions and breaking the cycle. If the universe has already undergone an infinite number of cycles, then it should have already reached a state of maximum entropy, which is not what we observe. This problem largely led to the abandonment of classical cyclic models in favour of a universe with a distinct beginning, like the Big Bang. The advent of modern quantum cosmology, however, has reopened the door for cyclic models by offering potential solutions to the entropy problem and the singularity problem. The Big Bounce theory, discussed previously, is a prime example of a modern cyclic model rooted in quantum gravity, specifically loop quantum gravity. In the Big Bounce, the universe does not collapse to an infinite density singularity, a big crunch, but reaches a finite maximum density before quantum gravitational effects cause it to rebound. This finite bounce might offer a way to avoid the increasing entropy issue, although this remains an active area of debate among physicists. Some proposals suggest that the entropy from the previous cycle is effectively flushed away or diluted during the quantum bounce, allowing each new cycle to start with fresh low-entropy conditions. Another prominent class of modern cyclic models arises from brain cosmology, a framework derived from string theory. These models, often called ekpyrotic or cyclic universe models, propose a fundamentally different mechanism for the Big Bang. Instead of a singular beginning of time, these models suggest that our four-dimensional universe exists as a brane, a higher dimensional membrane, floating within a larger, higher dimensional space called the bulk. In this scenario, the Big Bang is not an explosion from a point, but rather the result of a collision between two such branes, or an interaction between our brain and another brain in the bulk. In the ekpyrotic model, derived from the Greek word for conflagration, two branes slowly approach each other over a very long period. As they draw near, the gravitational interaction between them becomes strong, causing the branes to accelerate towards each other. Their collision releases enormous amounts of energy, which manifests as the hot, dense Big Bang phase of our universe. After the collision, the branes might bounce apart, expand and cool, and then slowly move back together over cosmic timescales, setting up the next collision and a new cycle. This model, proposed by Paul Steinhardt and Neil Turok, offers a potential solution to the entropy problem by suggesting that the universe undergoes a long, cold, and empty contracting phase between cycles, allowing entropy to be effectively diluted or minimized before the next bounce. These brane-world cyclic models also offer alternative explanations for cosmic phenomena typically addressed by inflation theory. For example, the smoothness and flatness of the universe and the origin of cosmic structure could arise from the properties of the brane collision itself, or from quantum fluctuations that occur during the long, slow contraction phase preceding the collision. This provides a compelling alternative to the inflationary paradigm for explaining the observed features of the cosmic microwave background. Different cyclic models vary in their specific mechanisms and predictions. Some propose that the universe eternally expands and contracts, others that it continues to expand for a vast period before collapsing, and some models suggest that the cycles are not perfectly identical but evolve over time. Common to all these models is the absence of a true beginning in time. Instead, the universe has always existed in some form, undergoing transformations. The motivation for exploring cyclic models is manifold. Beyond resolving the singularity problem and potentially the entropy problem, they offer a philosophical appeal of an eternal universe, avoiding the question of what came before the Big Bang by positing that there was always a before. They also provide a different theoretical laboratory for investigating fundamental physics, offering testable predictions that may distinguish them from other cosmological models. However, cyclic universe models, particularly the modern quantum gravity and brane world versions, remain highly theoretical and face significant challenges. Direct observational evidence that can definitively distinguish between a single Big Bang with inflation and a cyclic universe is still lacking. Scientists are actively looking for specific cosmological signatures, such as unique patterns in the cosmic microwave background, or the characteristics of gravitational waves, that could provide evidence for or against these cyclic scenarios. While the questions surrounding their viability persist, cyclic models continue to represent a vibrant and intriguing area of research, pushing the boundaries of our understanding of cosmic origins and the ultimate fate of the universe. The concept of brane worlds is a fascinating and highly speculative idea that emerges from string theory, one of the leading candidates for a theory of everything that aims to unify all fundamental forces of nature, including gravity. In string theory, the fundamental constituents of the universe are not point-like particles, but rather tiny, one-dimensional vibrating strings. The introduction of extra spatial dimensions beyond the three spatial dimensions and one time dimension we experience is a common feature of many string theory models. Brane-world cosmology takes this idea further, proposing that our entire universe is confined to a higher dimensional membrane, or brane, floating within a larger, higher dimensional space called the bulk, or multiverse. To understand the concept of a brane, it is helpful to use an analogy. Imagine a two-dimensional sheet of paper existing in a three-dimensional room. Creatures living on the paper can only move left, right, forward, or backward along the surface of the paper, they are unaware of the dimension extending up or down from their paper world. In the brain world scenario, our familiar 3 spatial dimensions, plus 1 time dimension, constitute such a brain which is embedded in a higher dimensional space. This higher dimensional space, the bulk, would contain extra spatial dimensions that we cannot perceive directly. The existence of these extra dimensions is a key prediction of string theory. While early string theories required 10 or 11 dimensions, brain world models often operate with a minimum of 5 dimensions, our 4-dimensional spacetime, the brain, and at least 1 extra spatial dimension, the bulk. The reason we do not observe these extra dimensions is usually explained in one of 2 ways. Either they are compactified or curled up into extremely tiny, unobservable loops at every point in our spacetime, or they are large, but our matter and forces are confined to the brain. In the brain world scenario, ordinary matter, protons, neutrons, electrons, and the forces that govern them, electromagnetism, strong nuclear force, weak nuclear force, are all confined to our 4-dimensional brain. This means that photons, electrons, and the particles that mediate the strong and weak forces cannot travel into the extra dimensions. They are stuck on our brain. However, gravity, according to this theory, is different. Gravity is described by the warping of spacetime itself, and in brain world models, gravity is thought to be able to leak or propagate into the extra dimensions of the bulk. This property has significant implications. One of the motivations for brain world models is to address the hierarchy problem in physics. The hierarchy problem refers to the vast difference in strength between gravity and the other 3 fundamental forces. Gravity is extraordinarily weak compared to electromagnetism, for instance. If all forces originated from a unified theory at high energies, why is gravity so much weaker at lower energies? Brain world models offer a possible solution. If gravity can propagate into extra dimensions while other forces are confined to our brain, then its effective strength on our brain would appear much weaker because its influence is spread out across a larger, higher dimensional space. This idea suggests that gravity is not inherently weak, but rather its strength is diluted by its access to the bulk. The concept of brain worlds also provides a radical new perspective on the origin of the universe and the Big Bang. In some brain world models, such as the ekpyrotic or cyclic universe models, the Big Bang is not an explosion from a singularity, but rather the result of a collision between 2 or more brains. Imagine our universe's brain slowly approaching another parallel brain in the bulk. As these brains draw closer, their gravitational interaction increases, eventually leading to a collision. This collision, or bounce, releases enormous amounts of energy, which then manifest as the hot, dense Big Bang phase that expands and cools into our universe. After the collision, the brains might separate again, expanding and cooling, only to eventually move back together for another collision, leading to a cyclical universe. This offers an alternative to cosmic inflation for explaining the flatness and uniformity of the universe and the origin of cosmic structure, which could arise from the collision itself or from quantum fluctuations on the brains during their slow approach. Another intriguing implication of brain world models is the potential for dark matter to reside on a different brain or in the bulk. If dark matter particles are not confined to our brain but interact only gravitationally, or are located on a nearby shadow brain, it could explain why we cannot detect them through electromagnetic interactions. Their gravitational influence would still be felt on our brain, accounting for the observed gravitational effects of dark matter in galaxies and clusters. Brain-world cosmology is an active area of theoretical research, but it remains highly speculative. There is currently no direct experimental evidence to confirm the existence of extra dimensions or brains. Scientists are exploring potential ways to test these ideas. For example, if extra dimensions are large, they might manifest themselves as subtle deviations from Newton's law of gravity at very small distances, which could be detectable in precision experiments. Particle accelerators like the Large Hadron Collider could also potentially produce exotic particles that indicate the existence of extra dimensions, or even miniature black holes that rapidly evaporate if gravity is strong at small scales due to extra dimensions. The mathematical consistency and elegance of string theory and its brain world extensions continue to make them compelling candidates for a unified theory of physics. While the concepts are abstract and far removed from everyday experience, They offer profound new ways of thinking about the universe's structure, its origin, and our place within a potentially much larger, multi-dimensional cosmos. The idea that our universe is merely a slice or a membrane within a grander cosmic architecture challenges conventional notions of reality and fuels the ongoing quest for a deeper understanding of the fundamental nature of space-time and matter. The standard Big Bang theory describes the universe expanding from an extremely hot and dense state, often extrapolated back to an initial singularity where the laws of physics break down. This unresolved singularity has led physicists to explore alternative scenarios for the universe's origin. One such intriguing concept arises from string theory, specifically within the framework of brane cosmology, where the Big Bang is not a singular point in time, but rather the result of a collision between higher dimensional membranes, or branes. To grasp the idea of colliding branes, one must first understand the concept of a brane itself. In string theory, the fundamental constituents of reality are not point-like particles, but tiny, vibrating one-dimensional strings. For string theory to be mathematically consistent, it requires the existence of extra spatial dimensions beyond the three we experience every day, plus the one dimension of time. While these extra dimensions might be curled up to an unobservably small size, some string theory models propose that they are large, and our entire universe is confined to a four-dimensional surface, or brane, embedded within this larger, higher dimensional space, often called the bulk. In this brane world scenario, all the particles that make up ordinary matter, like electrons and quarks, and the forces that govern their interactions, electromagnetism, the strong nuclear force and the weak nuclear force, are confined to our brane. They cannot travel into the extra dimensions. However, gravity, being a manifestation of the curvature of space-time itself, is thought to be able to propagate into these extra dimensions. This distinction is crucial for the colliding brane models of the Big Bang. The most prominent example of a colliding brane model is the ekpyrotic universe scenario, which later evolved into cyclic universe models, proposed by physicists Paul Steinhardt and Neil Turok, among others. The term ekpyrotic comes from an ancient Greek word meaning conflagration, or cosmic fire, referring to a universe that is born from fire and returns to fire. In the ekpyrotic model, our universe is a three-dimensional brane that exists parallel to at least one other three-dimensional brane in a higher dimensional bulk. These two branes are not static. They are slowly moving towards each other. This approach phase is characterized by a long period of slow contraction of the universe, which is very different from the standard Big Bang's initial expansion. During this slow contraction, the universe is cold, empty, and nearly flat. This long, cold phase allows for the smoothing out of any initial irregularities and the natural generation of the seeds of cosmic structure. As the two branes slowly draw closer, their gravitational interaction becomes increasingly strong. This gravitational attraction pulls them together, causing them to accelerate towards each other. The climactic event in this model is the collision of these two branes. This collision is not a gentle touch, it is a violent high-energy impact. The immense kinetic energy of the colliding branes is converted into the matter and radiation that fill our universe. This sudden release of energy, and the subsequent rapid expansion of our brane, is what we perceive as the Big Bang. So in this view, the Big Bang is not the absolute beginning of time from a singularity, but rather a violent energetic event that marks a transition from a previous phase of cosmic history. The collision effectively reheats the universe, creating the hot, dense conditions that the standard Big Bang theory describes. After the collision, the branes are thought to bounce apart, and our universe enters a new phase of expansion. This expansion continues for an incredibly long time, during which stars and galaxies form, evolve, and eventually die. As the universe expands and becomes increasingly dilute, the branes slowly begin to drift back towards each other, driven by forces within the bulk. This sets the stage for the next collision, initiating a new Big Bang and a new cycle of cosmic evolution. This makes the ekpyrotic model a type of cyclic universe, where the cosmos undergoes an endless series of collisions, expansions, and contractions. One of the significant advantages claimed by colliding brane models is their potential to address some of the puzzles that cosmic inflation was introduced to solve, without necessarily relying on inflation itself. For instance, the flatness problem, why the universe is so spatially flat, can be explained by the long, slow contraction phase preceding the collision. During this phase, any initial curvature of the brane would be squeezed out, making it appear flat at the moment of collision and subsequent expansion. The horizon problem, why distant regions of the cosmic microwave background have the same temperature, can also be addressed. In the ekpyrotic model, these regions were in causal contact during the slow, pre-collision contraction phase, allowing them to reach thermal equilibrium before the Big Bang event. Furthermore, the origin of the seeds of cosmic structure, the tiny density fluctuations that grew into galaxies, can also be explained by quantum fluctuations occurring on the branes during their slow approach, or at the moment of collision. These models predict a slightly different spectrum of density fluctuations compared to inflationary models, which could potentially be a way to distinguish between them through precise observations of the cosmic microwave background and large-scale structure. It is important to note that colliding brane models are highly theoretical and remain speculative. The existence of extra dimensions and branes has not been experimentally confirmed. While these models offer elegant solutions to some cosmological problems and provide an alternative to the Big Bang singularity, they introduce new complexities and require further development. Observational tests are challenging, as they often rely on detecting subtle signatures in the cosmic microwave background or gravitational waves that would be distinct from those predicted by inflationary Big Bang models. Despite these challenges, the concept of colliding branes represents a powerful and imaginative attempt to push the boundaries of our understanding of cosmic origins, suggesting that our universe might be part of a much grander, multi-dimensional cosmic ballet. The concept of a multiverse suggests that our universe is not the only one, but rather one of many, perhaps an infinite number of universes. This idea, once relegated to the realm of science fiction, has gained increasing traction among theoretical physicists as a potential consequence of various cosmological and quantum theories. The multiverse hypothesis offers profound implications for our understanding of existence, the laws of physics, and our place in the cosmos. The term multiverse encompasses several distinct theoretical concepts, each arising from different areas of physics. It is not a single unified theory, but a collection of scenarios where multiple universes exist. These different types of multiverses can be broadly categorized, though there is some overlap. One type of multiverse arises from the idea of an infinite universe. If space is truly infinite and contains an infinite amount of matter and energy, then according to the laws of probability, everything that can possibly happen will happen an infinite number of times. This implies that there would be infinitely many patches of space, identical to our observable universe, and even infinitely many patches where events unfolded slightly differently. This is often referred to as a level 1 multiverse. In this scenario, the other universes are simply very distant regions of the same, infinitely large universe, beyond our observable horizon. They obey the same physical laws but may have different arrangements of matter. A more complex and often discussed type of multiverse emerges from cosmic inflation, particularly the concept of eternal inflation. This will be elaborated upon in the next section, but in brief, eternal inflation suggests that the process of inflation, which rapidly expanded the early universe, never truly stops everywhere. Instead, it continues indefinitely in some regions, constantly spawning new bubble universes within a vast, ever-inflating background. Each of these bubble universes could have different initial conditions, and potentially even different fundamental physical constants or laws, depending on how the inflationary field decays. This is a level 2 multiverse, where universes can have different physical properties. Another source of multiverse ideas comes from string theory and its extensions, such as M theory. These theories suggest the existence of extra spatial dimensions and a vast number of possible ways these dimensions can be compactified or curled up. Each way of compactifying the extra dimensions could lead to a different set of physical laws and constants in the resulting 4-dimensional universe. This creates a landscape of possible universes, potentially an enormous number, each with its own unique characteristics. Our universe would simply be one point in this vast landscape of possibilities. This also falls under the Level 2 multiverse category. The brain world scenario, where our universe is a membrane in a higher dimensional space, also naturally leads to multiverse concepts, as there could be other brains existing in the same bulk, representing other universes. The many worlds interpretation of quantum mechanics offers a different kind of multiverse, sometimes called a Level 3 multiverse. This interpretation suggests that every time a quantum measurement is made, and a quantum system is forced to choose between multiple possible outcomes, e.g., an electron spin being up or down, the universe splits into multiple parallel universes, with each outcome realized in a different universe. In this view, all possible quantum outcomes are physically realized in some universe. These universes are not separated by vast distances in space, but are parallel in a more abstract quantum sense, constantly branching off from each other. This interpretation is distinct from the cosmological multiverses, as it arises from quantum events within a single, overarching quantum reality. Finally, some theoretical physicists propose a Level 4 multiverse, known as the mathematical universe hypothesis. This extreme idea suggests that all mathematically consistent structures correspond to actual universes. In this view, our universe is just one of many mathematical structures that exist, and there is no deeper reality beyond mathematics. The multiverse idea, particularly the Level 2 cosmological multiverses, offers a potential solution to the fine-tuning problem. The fine-tuning problem observes that the fundamental constants of our universe, such as the strength of gravity, the mass of the electron, the cosmological constant, appear to be incredibly finely tuned for the existence of stars, galaxies, and life. If these constants were even slightly different, the universe might be sterile, incapable of forming complex structures or supporting life. In a multiverse, this fine-tuning is not seen as a coincidence or evidence of design, but rather a statistical inevitability. If there are an immense number of universes, each with different physical constants, then it is not surprising that we find ourselves in one of the rare universes where the conditions are just right for our existence. This is an application of the anthropic principle, which states that the universe must have properties that allow for the existence of observers. Despite its explanatory power for certain cosmological puzzles, the multiverse idea remains highly speculative. A major challenge is the lack of direct observational evidence. By definition, other universes in many multiverse scenarios are causally disconnected from our own, making them difficult or impossible to observe directly. This raises questions about the scientific testability and falsifiability of the multiverse hypothesis. However, some theoretical predictions, such as the possibility of bubble universe collisions, leaving detectable imprints on the cosmic microwave background, are being explored as potential indirect tests. In conclusion, the multiverse idea is a profound and evolving concept in theoretical physics. It moves beyond the notion of a single, isolated universe, suggesting a vast landscape of cosmic realities. Whether arising from infinite space, eternal inflation, or the intricacies of string theory, the multiverse challenges our conventional understanding of cosmic uniqueness and offers a framework for addressing some of the deepest puzzles about the nature of our universe and its seemingly special properties. The theory of cosmic inflation, while incredibly successful in addressing several fundamental problems of the standard Big Bang model, paradoxically leads to one of the most mind-bending concepts in modern cosmology, the inflationary multiverse. This idea suggests that if inflation occurred in our universe, it might not have been a one-time event, but rather an eternal process, continuously generating an endless number of new, bubble universes, of which our own is just one. Let us first briefly revisit the concept of cosmic inflation. Inflation is a hypothetical period of extremely rapid, exponential expansion that is thought to have occurred in the first tiny fractions of a second after the Big Bang, perhaps from 10 to the power of minus 36 seconds to 10 to the power of minus 32 seconds. This rapid expansion was driven by a hypothetical energy field, often called the inflaton field. When the inflaton field eventually decayed, its energy was converted into the hot, dense matter and radiation that filled the universe, initiating the standard Big Bang expansion we observe today. Inflation elegantly solves the flatness problem, why the universe is spatially flat, the horizon problem, why distant regions of the cosmic microwave background are at the same temperature, and the magnetic monopole problem, the absence of hypothetical particles. The concept of an inflationary multiverse arises from certain properties of the inflaton field and the dynamics of inflation itself. In many inflationary models, the inflaton field does not decay uniformly or simultaneously everywhere. Instead, it fluctuates quantum mechanically. Due to the inherent quantum nature of fields, the inflaton field can fluctuate in its energy level. In some regions of space, the inflaton field might fluctuate to a higher energy state, causing inflation to continue. In other regions, it might fluctuate to a lower energy state, causing inflation to end and convert its energy into matter and radiation, forming a bubble universe. The key insight leading to eternal inflation is that the rate of expansion during inflation is so incredibly rapid that the regions where inflation continues expand exponentially faster than the regions where it ends. This means that even as some regions of space stop inflating and form new universes, the vast majority of the volume of space continues to inflate, creating ever more space for an endless number of new bubbles to form. It is like an endlessly branching tree, where each branch is a region of inflating space, and new leaves, bubble universes, are constantly budding off. This process is called eternal inflation because once it starts, it never truly stops everywhere. It is self-perpetuating. The inflating parent universe continually expands, creating new pockets where inflation ends, leading to the birth of new bubble universes. These bubble universes then expand according to the standard Big Bang model, forming stars, galaxies, and structures within their own boundaries. Our observable universe would be just one such bubble, a tiny patch within this much larger, eternally inflating cosmos. A crucial implication of the inflationary multiverse is that these different bubble universes are likely to have different properties. The way the inflaton field decays can vary from one bubble to another. This means that different bubble universes could have different fundamental physical constants, such as the strength of the fundamental forces, the masses of elementary particles, or even different numbers of spatial dimensions, though most models assume 3 large spatial dimensions. For example, if the value of the cosmological constant, dark energy, is determined by the specific vacuum state of the inflaton field, then different bubbles could have vastly different amounts of dark energy. This diversity of universes provides a compelling, albeit controversial solution to the fine-tuning problem. As noted, the physical constants in our universe appear to be remarkably finely tuned for the existence of life. If, for instance, the strong nuclear force was slightly weaker, atomic nuclei would not hold together. If it were slightly stronger, hydrogen would have fused into helium too quickly, and stars would not have lasted long enough for life to evolve. In an inflationary multiverse, the apparent fine-tuning of our universe is simply a statistical consequence. If there are an infinite number of universes with varying physical laws and constants, then it is not surprising that we find ourselves in one of the rare universes where the conditions are just right for complex structures and life to emerge. We exist in the universe that allows for our existence. This is often referred to as the anthropic principle applied to the multiverse. The inflationary multiverse is a theoretical prediction of many leading inflationary models, but it is extremely difficult to test directly. By definition, these other bubble universes are causally disconnected from our own. Light and information from them cannot reach us because the space between them is inflating exponentially fast. This raises questions about the scientific testability and falsifiability of the multiverse hypothesis. However, some researchers are exploring potential indirect signatures. For example, if our bubble universe once collided with another bubble during its early expansion, it might have left a subtle imprint on the cosmic microwave background, such as a cold spot or a specific pattern of anisotropies. Detecting such an imprint would provide compelling, though still indirect, evidence for the existence of other universes. Despite the challenges of direct verification, the inflationary multiverse concept is widely discussed in theoretical cosmology because it arises naturally from a theory, inflation, that is otherwise highly successful in explaining observed features of our universe. It pushes the boundaries of our understanding of cosmic reality, suggesting that our universe is not unique, but part of an unimaginably vast and diverse collection of cosmic bubbles, each with its own history and properties. It transforms the question of what caused the Big Bang into a question of what caused the eternal inflation that spawns countless Big Bangs. The concept of a multiverse, where our universe is but one of many, opens up a vast realm of speculation about what these other universes might be like. Depending on the specific type of multiverse model, the characteristics of these parallel or distant universes could range from being almost identical to our own to being radically different, governed by entirely alien physical laws, or even possessing a different number of spatial dimensions. In the simplest form of a multiverse, often called a level 1 multiverse, these other universes are simply very distant regions of our own infinitely large universe. If space extends infinitely, and the distribution of matter and energy is roughly uniform on very large scales, then statistically, there must be regions far beyond our observable horizon that are identical to our own observable universe, or at least contain similar arrangements of matter. In this scenario, the physical laws and fundamental constants would be the same as ours, but the specific configurations of particles and fields would vary. Given infinite space, any possible arrangement of matter that can exist will eventually repeat. So, in this type of multiverse, there could be another Earth, another Milky Way, or even another version of you simply located an unimaginably vast distance away. These are not truly other universes in the sense of having different laws, but rather extremely distant copies or variations within the same overarching universe. A more profound difference arises in level 2 multiverses, which are often predicted by theories like eternal inflation or string theory's landscape. In these scenarios, the fundamental physical laws and constants can vary from one universe to another. Consider the inflationary multiverse. As discussed, eternal inflation suggests that new, bubble universes are constantly budding off from a larger ever-inflating background. The specific properties of each bubble universe depend on how the infleton field decays within that particular region. This decay process could lead to different values for fundamental constants. For example, different fundamental constants, the strength of the 4 fundamental forces, gravity, electromagnetism, strong and weak nuclear forces, could vary. Imagine a universe where the electromagnetic force is much stronger, atoms might be unstable, or chemical reactions might proceed entirely differently, making complex chemistry impossible. Conversely, if it were too weak, electrons might not bind to nuclei, preventing atom formation. The masses of fundamental particles like electrons and quarks could also differ. If the electron were much heavier, atoms might collapse. If quarks were much lighter, protons and neutrons might not form stable nuclei. The cosmological constant which drives the accelerated expansion of our universe could also take on vastly different values, leading to universes that either expand too rapidly for structures to form or collapse almost immediately. Different particle content. The types of fundamental particles themselves might vary. Perhaps some universes have different sets of quarks and leptons, or entirely new types of particles that do not exist in our universe. This would lead to entirely different forms of matter and energy. Different spatial dimensions. While our universe appears to have 3 large spatial dimensions and 1 time dimension, string theory suggests that there could be many more. In some inflationary or string theory models, the number of large, uncompactified spatial dimensions could vary from one universe to another. A universe with only 2 spatial dimensions would be a flat plane, where complex structures like stars and planets might not be able to form due to gravitational collapse. A universe with 4 or more large spatial dimensions would have vastly different gravitational laws and orbital mechanics, likely preventing stable planetary systems or even atoms from forming. Different initial conditions. Even if the fundamental laws are the same, the initial distribution of matter and energy could vary. Some universes might be born with much greater initial density fluctuations, leading to a universe dominated by massive black holes, or so smooth that no structures form. The string theory landscape also contributes to the idea of diverse universes. String theory requires extra spatial dimensions, which are typically compactified or curled up into tiny shapes. The way these extra dimensions are curled up determines the specific physical laws and constants we observe in our four-dimensional universe. String theory suggests there are an enormous number of ways, perhaps 10 to the power of 500 or more, to compactify these dimensions, each corresponding to a different vacuum state and thus a different set of physical laws. Each of these different compactifications could represent a distinct universe within the multiverse. Our universe would simply be one specific valley in this vast landscape of possibilities. In these level 2 multiverses, the other universes are truly separate entities, often causally disconnected from our own. We cannot travel to them, nor can we send signals to them, because the space between them is either expanding too rapidly, as in eternal inflation, or they exist in different inaccessible regions of the higher dimensional bulk. The many-worlds interpretation of quantum mechanics, a level 3 multiverse, presents a different kind of other universe. In this view, every time a quantum measurement is made and a quantum system's wave function collapses into a definite state, the universe splits into multiple parallel universes. Each possible outcome of the quantum measurement is realized in a different universe. For example, if a photon can either pass through a slit or be reflected, then in one universe it passes through, and in another it is reflected. These universes are not spatially separated but exist in a quantum superposition, constantly branching. In this scenario, all universes would share the same fundamental physical laws, but their histories and specific events would diverge at every quantum choice point. This leads to an unimaginably vast number of parallel realities, where every possible outcome of every quantum event is realized somewhere. Finally, the mathematical universe hypothesis, a level 4 multiverse, is the most abstract. It posits that every mathematically consistent structure corresponds to a real, existing universe. In this view, the physical laws and constants of other universes would simply be different mathematical structures. The speculation about other universes is driven by a desire to explain why our universe has the specific properties it does, particularly the fine-tuning that allows for life. If there are countless universes with varying properties, then it is not surprising that we find ourselves in one that is hospitable to our existence. While these ideas are largely theoretical and lack direct observational confirmation, they represent a frontier in our understanding of cosmic reality, pushing the boundaries of what is possible and challenging our anthropocentric view of the cosmos. The fine-tuning problem is one of the most intriguing and perplexing puzzles in modern cosmology and fundamental physics. It refers to the observation that the fundamental constants of nature and the initial conditions of the universe appear to be remarkably precise, or tuned, to allow for the existence of stars, galaxies, and ultimately life as we know it. If these constants or conditions were even slightly different, the universe would be a radically different place, likely inhospitable to any form of complex structure or life. This apparent precision raises profound questions about chance, necessity, or design. Let's consider some examples of these finely tuned parameters. The strength of the strong nuclear force is critical. This force binds quarks into protons and neutrons and holds protons and neutrons together in atomic nuclei. If it were just a few % weaker, stable atomic nuclei beyond hydrogen couldn't form, preventing the existence of all heavier elements necessary for chemistry and life. Conversely, if it were slightly stronger, hydrogen would have fused into helium too rapidly in the early universe, leaving no hydrogen to fuel long-lived stars like our Sun, which are essential for the gradual evolution of life. Similarly, the strength of the electromagnetic force governs interactions between charged particles, holding electrons in orbit around atomic nuclei. If this force was significantly stronger, electrons would be pulled too tightly to the nucleus, preventing chemical bonds and complex molecules from forming. If it were weaker, electrons might not bind to nuclei at all, making atoms impossible. The mass difference between protons and neutrons is another crucial parameter. Neutrons are slightly more massive than protons, by about 0.1% of their mass. If neutrons were slightly less massive than protons, all protons would have decayed into neutrons in the early universe, leading to a universe composed only of neutrons, with no hydrogen to form stars or water. If the mass difference were larger, neutrons would decay too quickly before they could form helium, again leading to a universe without heavier elements. The cosmological constant, representing the energy density of empty space and responsible for the universe's accelerating expansion, is also incredibly precise. Observations suggest its value is extremely small, yet non-zero. Theoretical predictions for its value, based on quantum field theory, are vastly larger, by a factor of 10 to the power of 120, than what we observe. If the cosmological constant were much larger and positive, the universe would have expanded so rapidly in its early moments that matter would have been too diluted to form stars and galaxies. If it were negative and larger, the universe would have quickly collapsed back on itself. The observed value is incredibly precise, allowing for structure formation over billions of years. Furthermore, the initial density fluctuations, the tiny variations in density imprinted on the cosmic microwave background that served as the seeds for cosmic structure, also appear to be finely tuned. If these fluctuations were too small, gravity wouldn't have been strong enough to pull matter together to form stars and galaxies. If they were too large, the universe would have quickly collapsed into massive black holes, leaving no stable structures. Lastly, the number of spatial dimensions in our universe, which is 3 large spatial dimensions, is vital. If there were fewer, like 2, gravity would behave differently, making stable orbits for planets impossible. If there were more, such as 4 or more large dimensions, planetary orbits would be unstable, and atoms themselves might not be stable, as electrons would spiral into the nucleus. The cumulative effect of these seemingly precise values is what constitutes the fine-tuning problem. It appears as if the universe's fundamental parameters were set with extreme precision to allow for the existence of complexity and life. This observation prompts several lines of thought. One possibility is coincidence or luck, that the fine-tuning is simply an incredibly improbable coincidence. We are just extraordinarily lucky to exist in a universe where the numbers happen to fall into the narrow range required for life. However, the sheer improbability of so many independent parameters being precisely tuned makes this explanation unsatisfying for many scientists. Another possibility is necessity, that there is a deeper, currently unknown theory that dictates these constants must have the values they do. If such a theory of everything were discovered, it might show that the seemingly arbitrary values are, in fact, uniquely determined by fundamental principles. However, no such theory has been developed yet that explains all the constants. For some, the fine-tuning points towards design, a designer or creator who intentionally set these parameters for the universe to be life-permitting. This is a theological or philosophical interpretation that lies outside the realm of scientific inquiry, as it is not testable or falsifiable by scientific methods. The most common scientific explanation for fine-tuning is the multiverse hypothesis. If our universe is just one of an enormous, perhaps infinite number of universes, and if these other universes have different fundamental constants and laws, then it is not surprising that we find ourselves in one of the rare universes where the conditions are suitable for life. In this scenario, there is no tuning involved. It is simply a matter of selection bias. We can only observe universes that permit observers. This concept is closely tied to the anthropic principle, which will be discussed in the next section. The fine-tuning problem remains a significant challenge and a powerful motivator for research in fundamental physics and cosmology. It pushes scientists to explore new theories, such as string theory and inflationary cosmology, that might naturally lead to a vast landscape of possible universes, or to discover deeper principles that constrain the values of these constants. Regardless of the ultimate explanation, the apparent fine-tuning of our universe highlights the delicate balance of physical laws that allow for the existence of complexity, consciousness, and the very possibility of asking such profound questions. The anthropic principle is a philosophical and scientific concept that attempts to address the fine-tuning problem, which observes that the fundamental constants and laws of our universe appear to be remarkably precise for the existence of life. Rather than trying to explain why these constants have their specific values, the anthropic principle suggests that we observe the universe to have the properties it does simply because only in such a universe could observers like us exist. It is a statement about the relationship between the universe and the presence of intelligent observers within it. The anthropic principle appears in 2 main forms: the weak anthropic principle, WAP, and the strong anthropic principle, SAP. The WAP is less controversial and more widely accepted. It suggests that the physical and cosmological properties of the universe are not random but instead fall within a narrow range that allows for the emergence of carbon-based life. In other words, the universe must have certain characteristics, like the right rate of expansion or age, because if it didn't, observers like us wouldn't exist to notice it. The WAP doesn't attempt to explain why the universe is life-permitting, but rather highlights the observational bias in our existence. It's often discussed alongside the multiverse theory. If countless universes exist, each with varying physical laws, it's no surprise we find ourselves in one that happens to support life. In contrast, the strong anthropic principle, SAP, is more speculative and controversial. It takes the argument further by claiming that the universe must have the properties necessary for life to eventually develop. This implies that the emergence of observers is not just a consequence of the universe's conditions, but may actually be a fundamental feature or purpose of the universe itself. Some interpretations of the SAP suggest that the universe is in some way designed or inherently directed toward producing conscious observers, raising philosophical and metaphysical questions about purpose and necessity in the cosmos. The SAP can be interpreted in various ways. One interpretation suggests that there is an underlying law or principle that forces the universe to evolve in a way that leads to the emergence of life. Another, more radical interpretation, sometimes called the participatory anthropic principle, suggests that observers are necessary to bring the universe into existence, perhaps by collapsing quantum wave functions or by somehow actualizing physical reality. These stronger forms of the anthropic principle often venture into philosophical or theological territory and are not generally considered testable scientific hypotheses in the same way as the WAP. The anthropic principle is not a predictive scientific theory in the traditional sense. It does not provide a mechanism for explaining how the universe came to be finely tuned. Instead, it offers a framework for interpreting the observed fine-tuning. It shifts the question from why is the universe so perfectly suited for life, to given that we exist, what must the universe be like? The anthropic principle has found application in various scientific contexts, influencing how physicists interpret observed cosmic phenomena. For instance, it has been used in predicting cosmic parameters. In some cases, even before direct observational evidence, physicists have employed anthropic arguments to anticipate the values of certain cosmological features. A notable example is the cosmological constant. Some physicists suggested it must be incredibly small, arguing that a larger value would prevent the formation of galaxies, thus making life impossible. The principle is also crucial in interpreting the multiverse. If a multitude of universes exists, each with different properties, then our presence in a universe perfectly suited for life isn't a miraculous coincidence, but a statistical inevitability. Our existence simply selects for the specific universe or region that supports life, sidestepping the need for a deliberate design and explaining apparent fine-tuning through this concept of statistical sampling. Furthermore, the anthropic principle encourages a deeper understanding of fundamental physics, prompting researchers to investigate how the underlying laws and constants of the universe might inherently connect to the emergence of complexity in life itself. However, the anthropic principle also faces criticism. Some argue that it is unfalsifiable, meaning it cannot be proven wrong, which makes it less scientific. Critics also contend that it is an argument of last resort, an admission that we cannot explain the fine-tuning through fundamental physics. It can also be seen as a form of circular reasoning. The universe is suitable for life because we are here to observe it. Furthermore, the definition of life, or observer, can be vague, leading to ambiguity. Despite these criticisms, the anthropic principle serves as a powerful reminder of the profound connection between the universe's fundamental properties and the existence of observers within it. It highlights the unique conditions that allow for complexity to emerge from the simplicity of the early cosmos. While it may not provide a causal explanation for the universe's fine-tuning, it offers a framework for understanding why we find ourselves in a universe that appears so remarkably hospitable to life, especially when considered in the context of a potentially vast and diverse multiverse.